Welcome everyone. It's wonderful to have you here. Before we get started, would you let us know in the comments where you're tuning in from and the time of day it is for you? I love seeing how this space brings together people from across the globe. A heartfelt thank you as well to all who've subscribed and supported the channel. It helps me know what connects with you, and it helps others discover these calming moments too. And if inspiration strikes, please feel free to leave your ideas for future videos. With that said, let's begin. Chapter 1. Understanding the Uncertainty Principle. In the realm of quantum mechanics, one concept stands out like a lighthouse in a foggy night, its light illuminating the shadows of uncertainty. This is the uncertainty principle, a cornerstone of quantum theory that reshapes our understanding of the microscopic world. Imagine standing at the edge of a vast ocean, where the waves of possibility crash against the shore of certainty, each wave a reminder that what we think we know is but a fragment of a deeper truth. The uncertainty principle, fundamentally, states that certain pairs of physical properties like position and momentum cannot be simultaneously measured with arbitrary precision. This means that the more accurately we measure one property, the less accurately we can determine the other. Picture a delicate balance. If you lean toward one side, the other inevitably tilts away. This principle is not merely a reflection of the limitations of our instruments. It reveals something intrinsic about the nature of reality itself. To grasp the origins of this profound idea, we must journey back to the early 20th century, when the landscape of physics was undergoing a radical transformation. Traditional Newtonian mechanics, with its predictable paths and deterministic equations, was beginning to show cracks under the weight of new discoveries. As scientists peered deeper into the atomic realm, they were greeted not by the orderly universe they expected, but by a chaotic ballet of particles behaving in ways that defied intuition. At the forefront of this revolution was Werner Heisenberg, a German physicist whose name would become synonymous with the uncertainty principle. In the summer of 1927, Heisenberg published a paper that would forever alter physics. His work arose from the need to understand the behavior of electrons, which seemed to flit about their atomic orbits like fireflies in the night, unpredictable and ephemeral. Heisenberg's efforts were rooted in his realization that the act of measurement itself interferes with the system being observed. This insight led him to articulate a groundbreaking relationship between position and momentum. He famously stated, "What we observe is not nature itself, but nature exposed to our method of questioning." This quote encapsulates the essence of the uncertainty principle. It underscores that our interaction with the quantum world inevitably alters the very phenomena we seek to study. Consider for a moment the implications of Heisenberg's assertion. Imagine attempting to measure the position of a tiny particle, say an electron. To do so, you might shine light upon it. However, the very act of shining light, of probing the particle, introduces energy that alters its momentum. The more precisely you wish to pinpoint its location, the more energy you impart, and thus the greater the uncertainty in its momentum. This delicate interplay illustrates the fundamental limits of our measurements and beckons us to reconsider our understanding of reality. The uncertainty principle also challenges the classical worldview, where objects possess definite properties independent of observation. In the quantum realm, particles exist in states of probability until we observe them. This concept can be difficult to digest. It implies that reality at its core is not as solid as our everyday experiences suggest. As physicist Niels Bohr, a contemporary of Heisenberg, noted, "There are no quantum phenomena that do not change when we observe them." The implications of the uncertainty principle extend beyond mere measurements. They ripple through the very fabric of theoretical physics and our understanding of the universe. For instance, it suggests that particles can exist in multiple states at once, a phenomenon beautifully illustrated by the thought experiment known as Schrödinger's cat. This thought experiment posits a cat that is simultaneously alive and dead until it is observed, illustrating the paradox of superposition at the heart of quantum mechanics. As we reflect on the uncertainty principle, we can appreciate how it has paved the way for advancements in various fields, from quantum computing to cryptography. The principle underlines the limits of predictability in the quantum world, leading to technologies that harness these very uncertainties. We find ourselves in a time where the implications of quantum mechanics are not limited to theoretical musings but manifest in everyday technologies that shape our lives. The historical context surrounding the development of the uncertainty principle is crucial for appreciating its significance. The early 20th century was a period of intense scientific exploration. Alongside Heisenberg, figures such as Albert Einstein and Max Planck were grappling with the implications of quantum theory. Their dialogues often highlighted the tension between established physics and the new quantum paradigms, as they sought to reconcile the deterministic universe of classical physics with the strange, probabilistic nature of quantum mechanics. Einstein, though a champion of quantum theory, famously expressed his discomfort with its implications. He once remarked, "God does not play dice with the universe," reflecting his belief in an underlying order that quantum mechanics seem to undermine. This debate between determinism and probability sparked profound discussions and continues to resonate within the scientific community today. As we immerse ourselves in the depths of the uncertainty principle, we find ourselves contemplating not just the mechanics of particles, but the philosophy of existence. What does it mean for our understanding of reality when certainty gives way to ambiguity? How does this principle influence our view of the universe, where the very act of observation alters the observed? The uncertainty principle serves as a reminder that at the quantum level, the universe is a place of constant flux. It challenges us to embrace the unknown and to recognize that our perceptions, while shaped by our observations, are merely glimpses into a much larger and complex reality. In this dance between observation and existence, we are invited to explore the delicate balance between knowledge and uncertainty. As we move forward, let us hold on to the essence of this principle, which urges us to acknowledge the limitations of our perceptions while inspiring curiosity and wonder. The uncertainty principle is not merely a scientific concept. It is a profound invitation to explore the mysteries of the universe, to question the very nature of reality, and to embrace the beauty of uncertainty itself. The implications of the uncertainty principle extend far beyond the confines of the laboratory, seeping into our broader understanding of the universe. It invites us to reconsider the very nature of knowledge and how we acquire it. In a world where particles do not adhere to the stringent laws of classical physics, one might wonder, how do we reconcile our quest for certainty with an inherent uncertainty in the fabric of existence? Imagine a landscape where every step you take is shrouded in fog, where the path forward is obscured yet filled with potential. This is the essence of the quantum world, where the act of observation not only reveals but also distorts. Such a perspective was profoundly embodied by Richard Feynman, a luminous figure in the realm of physics. He remarked, "The thing that distinguishes man from animals is man's ability to make choices." His words resonate deeply within the context of quantum mechanics, emphasizing that even in the face of uncertainty, we possess the agency to make informed choices that guide our understanding and interactions with the world. As we delve into the historical context of the uncertainty principle, we witness a convergence of brilliant minds, each contributing to a mosaic of thought that would shape modern physics. Among them was Max Born, who played a pivotal role in interpreting the mathematical foundations of quantum mechanics. He introduced the idea that the wave function, a central concept in quantum theory, does not merely predict the behavior of a particle, but embodies a probability distribution, a map of potential outcomes rather than certainties. Born articulated, the interpretation of quantum mechanics is not a matter of logic, but a matter of experience. This perspective aligns beautifully with the uncertainty principle's assertion that inherent unpredictability is woven into the very fabric of quantum phenomena. Visualize a wave spreading out across a surface, each crest representing a possible state of a particle. This wave, much like the ocean's tide, ebbs and flows, suggesting that at any moment, the particle could manifest in myriad ways. Yet when we attempt to measure it, the wave collapses, revealing only one of those potential states, a phenomenon that profoundly shapes our understanding of reality. The act of measurement, then, becomes a transformative process, one that underscores the delicate interplay between observer and observed. How does this principle influence our technological advancements? In recent decades, the implications of the uncertainty principle have given rise to innovations such as quantum computing and quantum cryptography. These technologies harness the very uncertainties that once seemed to confound us, transforming them into tools of immense power. Quantum computers, for instance, operate on the principle of superposition, allowing them to process vast amounts of information simultaneously. They embody the essence of uncertainty as a resource rather than a limitation, challenging our notions of computation and efficiency. Moreover, the uncertainty principle has implications that reach into the realms of philosophy and metaphysics. It prompts us to consider the nature of reality itself. If particles exist in states of probability until observed, what does this imply about our own existence? Are our lives, too, shaped by the interplay of observation and reality? This profound inquiry can lead us toward a deeper understanding of consciousness and the universe. As physicist David Bohm suggested, the observer is the observed. This interconnectedness beckons us to explore the relationships between our perceptions and the world around us, inviting a more holistic view of existence. In contemplating the uncertainty principle, we find ourselves on a threshold between science and philosophy. It is a reminder of the limits of human understanding and the vastness of the unknown. Each grain of knowledge we gather is but a fragment of a much larger tapestry, one that continually unfolds before us. As we navigate through these complexities, we are encouraged to approach our inquiries with humility and wonder, embracing the mysteries that lie beyond our grasp. The uncertainty principle is not merely a scientific statement, but a profound invitation to explore the nature of existence itself. It challenges us to find beauty in ambiguity and to recognize that our quest for certainty is part of the larger narrative of the universe. In this interplay between knowledge and uncertainty, we discover the richness of inquiry, the joy of exploration, and the exhilarating potential of what lies beyond our understanding. As we continue to unravel the layers of this principle, let us remain open to the myriad possibilities that emerge from the tension between observation and reality. Each question we pose, each experiment we conduct, is an active engagement with the unknown. It beckons us to venture forth, not with the expectation of definitive answers, but with the understanding that every step into the uncertain is a step toward deeper insight and richer experiences. In the realm of quantum mechanics, uncertainty is not the enemy. Rather, it is a catalyst for discovery. The uncertainty principle teaches us to embrace the fluidity of existence, to see the universe not as a rigid structure, but as a living, breathing entity full of wonder and potential. As we move forward in our exploration of quantum phenomena, let us carry with us the spirit of curiosity, the courage to question, and the grace to accept that uncertainty is an intrinsic part of the journey. Chapter 2. Measuring Position and Momentum. Position and momentum, two fundamental properties of particles, exist in a relationship that is both intricate and revealing. They serve as complementary aspects of the quantum world, much like two sides of the same coin. Position refers to where a particle is located in space, while momentum provides insight into its motion and direction. It is essential to recognize that these properties cannot be fully understood in isolation. Instead, they are entwined in a delicate balance that reflects the very fabric of quantum mechanics. The uncertainty principle, a cornerstone of quantum theory, articulates this relationship with a profound simplicity. It tells us that the more precisely we determine the position of a particle, the less precisely we can know its momentum. This is not merely a limitation of our measuring tools, but a fundamental truth about the nature of particles themselves. Imagine trying to view a cloud through a window. The clearer your view of the cloud's shape and position, the harder it becomes to gauge its movement and speed. Conversely, if you focus on its movement, the details of its structure become hazy. This interplay between clarity and ambiguity exemplifies the essence of the uncertainty principle. The mathematical framework that defines this principle arises from the wave-particle duality inherent in quantum mechanics. Particles such as electrons can exhibit both wave-like and particle-like properties depending on how they are observed. When we measure a particle's position, we collapse its wave function, bringing it into a definitive state at a known location. Yet, this active measurement also disturbs the particle's momentum, leading to an inherent uncertainty in its velocity and direction. This duality extends to all quantum systems, illustrating the fundamental limits of our understanding in the quantum realm. Consider the famous experiment involving electrons passing through a double slit. When both slits are open, electrons create an interference pattern on a screen, revealing their wave-like nature. However, if we attempt to measure which slit an electron passes through, the interference pattern disappears, replaced by a pattern consistent with classical particles. In this moment, we are confronted with a profound truth. The act of measurement alters the very nature of what we are observing. It is a reminder that in the quantum world, the observer is an integral part of the unfolding reality. This delicate interplay between position and momentum leads to intriguing limitations in measurement. In quantum systems, particles exist in a probabilistic state, characterized by a wave function that encodes the likelihood of finding a particle in various locations and states of motion. When we attempt to measure position with great precision, we collapse the wave function into a specific state, but this collapse introduces uncertainty into the momentum. Imagine trying to pinpoint the location of a butterfly as it flutters through a garden. If you focus intently on its position, the butterfly's movement becomes elusive, darting unpredictably from flower to flower. This is the essence of quantum measurement. The more closely we seek to capture one aspect, the more we lose grip on another. Renowned physicist Werner Heisenberg, who formulated the uncertainty principle, once reflected on the nature of measurement in quantum mechanics. He famously stated, "What we observe is not nature itself, but nature exposed to our method of questioning." This quote encapsulates the philosophical depth of our inquiry into the quantum realm. Every measurement we take is not simply a reflection of an objective reality, but a manifestation of our interaction with it. The quest for precision is, therefore, a dance with uncertainty, as we navigate the delicate balance between knowing and not knowing. The implications of this principle extend beyond theoretical musings. They reverberate through the very fabric of technology and our understanding of the universe. Quantum systems, such as atoms and subatomic particles, behave in ways that challenge our classical intuitions. For instance, consider the implications for quantum computing, where qubits harness the principles of superposition and entanglement. The precision required in manipulating qubits is inherently tied to the uncertainties described by the uncertainty principle. As researchers strive to push the boundaries of computation, they must grapple with the limitations that arise from these complementary properties. As we explore the depths of quantum systems, we encounter fascinating examples that illustrate the measurement limitations inherent in this domain. Take, for instance, the phenomenon of quantum entanglement, where two particles become linked in such a way that the state of one instantaneously influences the state of the other, regardless of the distance separating them. When measuring the position of one entangled particle, we gain information about its counterpart's position, yet this measurement simultaneously blurs our understanding of their momenta. The intricate dance of entangled particles serves as a testament to the interconnectedness of position and momentum, illustrating how our inquiries into one aspect ripple through the entire system. Imagine now a scenario involving a laser beam shining through a cloud of gas particles. As the beam interacts with the particles, we can measure their positions with remarkable accuracy. However, this measurement alters the momentum of the particles, scattering them in unpredictable directions. The more we try to focus on their positions, the more their movements become a fog of uncertainty. This is not merely an inconvenience, it is a fundamental characteristic of the quantum world. It invites us to ponder, how can we ever truly know the state of a system when our very act of observation transforms it. The relationship between position and momentum extends to the concept of wave packets, which represent localized groups of waves that describe a particle's behavior. These wave packets illustrate how particles do not exist in fixed positions, but rather as spread-out entities governed by probabilities. When we measure position, we effectively narrow down the wave packet, tightening our grasp on where the particle is, but in doing so, we spread out its momentum, creating uncertainty. It is a beautiful yet perplexing aspect of quantum mechanics, reminding us that our understanding of particles is rooted in probabilities rather than certainties. As we deepen our exploration, we encounter the concept of quantum states, which can be represented mathematically as vectors in a complex space. The position and momentum of a particle are described by wave functions, which encode the probabilities of finding a particle in various states. When we measure one of these properties, we effectively project the quantum state into a particular dimension. This projection illuminates one aspect while casting shadows on others, embodying the essence of the uncertainty principle. Renowned physicist Richard Feynman once expressed, "The only thing that counts is the probability of the outcome." This statement echoes the core of quantum mechanics, where outcomes are not deterministic but probabilistic. As we contemplate the nature of measurement, we are reminded that the universe operates on a canvas of possibilities, where the brushstrokes of our observations shape the reality we perceive. Through the lens of quantum mechanics, we learn that measurement is an act of profound significance. It shapes our understanding of existence, revealing a world that is both intricate and mysterious. The interplay of position and momentum serves as a gateway to a deeper comprehension of the universe, urging us to embrace uncertainty as a vital aspect of our inquiry. As we continue our journey into the heart of quantum mechanics, let us remain open to the wonders that unfold, knowing that with each step, we are drawn closer to the mysteries of reality itself. In this intricate world of quantum mechanics, the implications of measurement limitations extend to various phenomena, each revealing more about the nature of reality. One such example is the concept of quantum superposition, where particles can exist in multiple states simultaneously until measured. This brings forth the question, how does our desire for knowledge affect the very fabric of what we seek to understand? Imagine a spinning coin suspended in the air. While it spins, it represents both heads and tails, a perfect embodiment of superposition. It is only upon catching the coin that we force it into one state or the other. Similarly, in quantum mechanics, particles such as electrons exist in a superposition of states until we measure them, collapsing their probability wave into a definitive position. This act of observation transforms the probabilities into certainties, illustrating the delicate dance between knowledge and uncertainty. The implications of this phenomenon reach far beyond theoretical constructs. They influence practical applications in quantum technology. Consider quantum cryptography, where the security of information relies on the principles of quantum mechanics. The act of measuring a quantum state can reveal any attempt at eavesdropping, as the very act of observation disturbs the system. Here, the uncertainty principle becomes a powerful tool, ensuring the integrity of information by highlighting the impact of measurement on the quantum system. As we examine these concepts, we can't help but wonder about the nature of reality itself. Are we merely observers, or do our measurements actively shape the universe? The work of physicists like John Wheeler hints at this profound question. He famously proposed that, quote, "No phenomenon is a phenomenon until it is observed." Such statements invite us to consider the role of consciousness in the quantum realm, suggesting that our very act of observation may hold more significance than we initially comprehend. This interplay between observer and observed extends to the realm of particles, behavior under different conditions. In quantum systems, particles can exhibit wave-like properties, leading to phenomena such as diffraction and interference. Imagine a gently rippling pond, where a pebble creates waves that spread out and overlap, forming intricate patterns. When particles, like electrons, pass through a barrier with two openings, they can interfere with themselves, creating a pattern of light and dark on a screen. However, if we attempt to measure which path they take, the interference pattern disappears, as if the act of observation has disrupted their harmonious dance. This phenomenon serves as a poignant reminder of the inherent limitations of measurement in the quantum realm. The more we strive to pin down the behavior of particles, the more we must acknowledge the uncertainties that arise. The duality of position and momentum manifests not only in theoretical explorations, but also in experiments that probe the very foundations of our understanding. As we reflect on the broader implications of these principles, we may consider their impact on the future of technology and our understanding of the universe. Quantum mechanics has paved the way for innovations such as quantum computing, promising to revolutionize how we process information. Yet, the precision required in these systems is intrinsically tied to the uncertainties inherent in quantum states. Researchers must navigate these challenges, seeking to harness the power of superposition and entanglement, while acknowledging the limits placed upon them by the uncertainty principle. Furthermore, the interplay of measurement and uncertainty fosters a deeper appreciation for the intricacies of the universe. It encourages a mindset that embraces ambiguity, recognizing that certainty is often an illusion in the quantum world. As we advance in our scientific endeavors, we are reminded of the importance of humility and curiosity, for the universe is a vast ocean of mysteries waiting to be explored. In this journey, we encounter remarkable individuals whose contributions illuminate our path. One such figure is Niels Bohr, who emphasized the philosophical ramifications of quantum mechanics. He once stated, quote, "We are not going to be able to get around the problems of the theory by making assumptions about the nature of reality." His insights inspire us to contemplate the fundamental questions that arise from our exploration of position and momentum. An essential aspect of understanding these properties lies in recognizing their probabilistic nature. Instead of viewing particles as fixed points, we must learn to perceive them as clouds of possibility, each representing a range of potential outcomes. This shift in perspective allows us to appreciate the beauty of uncertainty, inviting us to question the very fabric of our existence. As we continue to unravel the mysteries of quantum mechanics, we find ourselves drawn into an intricate web of relationships defined by the interplay of position and momentum. Each measurement we undertake serves as a thread, connecting us to the broader narrative of the universe. With every inquiry, we inch closer to the heart of reality, embracing the unknown with open arms. The journey through this quantum landscape is not merely an exploration of particles and waves. It is an invitation to delve into the essence of existence itself. The delicate balance between knowledge and uncertainty challenges our perceptions, urging us to engage with the world around us in new and profound ways. In this exploration, we are not just observers. We become active participants in the unfolding drama of the cosmos, weaving our own stories into the fabric of reality. As we embrace the complexity of quantum mechanics, let us remain mindful of the beauty that lies within uncertainty. The relationship between position and momentum serves as a reminder that the universe is full of surprises, beckoning us to explore its depths with wonder and curiosity. Each moment of discovery enriches our understanding, revealing layers of complexity that continually reshape our view of the cosmos. In this dance of particles and waves, we find not only scientific truth, but also a profound connection to the very nature of existence. As we move forward in our exploration, let us carry with us the insights gleaned from the interplay of measurement and uncertainty, allowing them to guide us on our quest for knowledge in the ever-expanding universe. Chapter 3: Quantum Mechanics and its Philosophical Implications. The exploration of quantum mechanics invites us to reconsider deep-seated beliefs about the nature of reality. One of the most significant philosophical implications arising from this field is the tension between determinism and indeterminism. In classical physics, the universe appeared to operate like a well-oiled clock, where every event followed logically from preceding ones. If we had complete knowledge of the initial conditions, we could predict future states with absolute certainty. Yet, as we delve into the quantum realm, this comforting notion begins to unravel. Imagine a world where not all events are predetermined, where the future can unfold in myriad ways based on an intricate web of probabilities. It is here that the concept of indeterminism takes root. Quantum mechanics introduces a universe filled with uncertainty, where the outcomes of certain experiments cannot be predicted with absolute certainty, only their probabilities. The very act of measurement influences the outcome, adding a layer of complexity to our understanding of causality. This is beautifully illustrated in the words of physicist Niels Bohr, who famously stated, "Everything we call real is made of things that cannot be regarded as real." This statement challenges the deterministic view by suggesting that at a fundamental level, reality might be constructed from events that are inherently probabilistic. As we contemplate the philosophical ramifications of quantum mechanics, we encounter different interpretations that attempt to make sense of this puzzling world. Two prominent interpretations, the Copenhagen interpretation and the many worlds interpretation, offer distinct perspectives. The Copenhagen interpretation, championed by Bohr and Werner Heisenberg, posits that quantum particles exist in a state of superposition until measured. It is only through observation that these particles choose a state, collapsing into a defined position or momentum. This leads to the intriguing notion that the observer plays a pivotal role in shaping reality. In contrast, the many worlds interpretation proposed by Hugh Everett III suggests a more radical perspective. According to this view, every possible outcome of a quantum event actually occurs, each in its own branching universe. Picture a cosmic tree, with branches extending into infinite possibilities, each one representing a different reality. This interpretation removes the randomness associated with measurement and asserts that all outcomes coexist. It paints a picture of a multiverse, where every choice and chance event spawns a new universe. This divergence between interpretations leads us to ponder, what does it mean to observe? The observer effect in quantum mechanics implies that the very act of measurement influences the system being observed. When we measure a particle's position, we inadvertently alter its momentum thanks to the uncertainty principle. The subtle interplay between observer and observed invites us to consider the profound implications of consciousness and reality. Are we mere spectators in a cosmic play, or do our observations actively shape the narrative? As we reflect on the uncertainty principle's challenge to classical physics, we recognize its profound impact on our understanding of reality. While classical physics offers a deterministic view, quantum mechanics introduces an intrinsic uncertainty that reshapes our worldview. The uncertainty principle reveals that at a quantum level, particles do not possess definite properties until measured. This realization evokes a sense of wonder, as it suggests that the universe is not a static tableau, but a dynamic interplay of possibilities. In classical terms, we might have envisioned particles as tiny billiard balls, colliding and interacting in predictable ways. However, the quantum world defies this simplistic view. Instead, particles are better understood as waves of probability, existing in a state of potential until they are observed. This conceptual shift is akin to watching a river flow. The water is constantly in motion, shaping its path as it interacts with the terrain around it. This fluidity challenges our classical intuitions and invites us to embrace a more nuanced understanding of nature. It raises questions about the very fabric of reality. Is it a deterministic clockwork, or is it a living, breathing tapestry of uncertainties? The philosophical implications resonate beyond the realm of physics, touching on questions of free will, consciousness, and the nature of existence itself. As we further explore the depths of quantum mechanics, we are reminded that these concepts are not merely abstract theories, but reflections of the world we inhabit. The uncertainty and indeterminism of quantum mechanics compel us to reconsider our relationship with the universe. We are not just passive observers, but active participants in a reality that is shaped by our perceptions and interactions. The journey through quantum mechanics is both a scientific inquiry and a philosophical exploration, beckoning us to ponder the mysteries that lie beyond our understanding. In this vast ocean of uncertainty, we may find comfort in the idea that not all is fixed. The universe unfolds in ways we may not yet comprehend, revealing an intricate dance of possibilities. As we continue this journey, let us remain open to the profound implications that quantum mechanics offers, embracing the beauty of uncertainty that lies at the heart of our existence. The philosophical implications of quantum mechanics extend into a profound contemplation about the nature of reality itself. As we ponder the tension between determinism and indeterminism, a question arises. What if the universe is not a predetermined script, but rather a fluid narrative that adapts and changes with each observation? This notion resonates with the idea that our understanding of the universe is intertwined with our very act of observing it. In the realm of quantum mechanics, the act of measurement has a transformative effect. When we measure a particle's position, we are not merely gaining information, we are altering the system. This phenomenon, known as the observer effect, adds an additional layer to our exploration of reality. The observer, in essence, becomes a participant in the cosmic dance, influencing the outcome of events in ways that challenge our classical understanding of causality. Consider the implications of this for our perception of free will. If our observations can influence quantum events, does that suggest a more active role in shaping our reality? The philosopher and physicist David Bohm once suggested that the universe operates as an interconnected whole, where the observer and the observed are in constant interplay. This perspective invites us to think of ourselves not as isolated entities, but as integral parts of the universe's unfolding story. As we embrace these ideas, we encounter the Copenhagen interpretation, which asserts that particles exist in a state of superposition, an amalgamation of potential outcomes, until an observation is made. This theory suggests that reality is not a static entity, but a dynamic spectrum of possibilities. It leads us to visualize particles as existing in a vast sea of potential, like a painter's palette, where the colors represent various outcomes waiting to be realized. The moment we choose a color, we bring forth a particular reality, shaping the canvas of existence. Yet, this interpretation has faced challenges and sparked debates among physicists and philosophers alike. The many-worlds interpretation, introduced by Hugh Everett, presents an alternative that diverges from the notions of collapse and superposition. It proposes an infinite array of universes, each representing a different outcome of quantum events. Imagine standing at a fork in the road, where every decision leads to a branching path, creating an intricate web of realities. Each choice we make, every measurement taken, births a new universe, suggesting that all possibilities coexist simultaneously. This radical perspective raises profound questions. Are there countless versions of ourselves living out every potential outcome? Does this realization diminish the significance of our choices? Or does it elevate them, suggesting that every decision creates ripples across an infinite landscape of realities? The many-worlds interpretation encourages us to visualize existence as a grand tapestry, each thread woven into the fabric of an ever-expanding multiverse. As we explore these interpretations, we must also confront the uncertainty principle's impact on our understanding of classical physics. The principle reveals that at a fundamental level, particles do not possess definitive properties until we measure them. This stands in stark contrast to classical physics, which assumes that objects have precise states independent of observation. The uncertainty principle invites us to consider the universe as a realm of possibilities, where certainty is an illusion. Imagine a delicate butterfly flitting through a garden. Its unpredictable flight path embodies the essence of quantum behavior, a dance of probabilities rather than certainties. This imagery serves as a reminder that the very act of measuring the butterfly's position will inevitably alter its trajectory, much like our observations shape the quantum world. Within this framework, The nature of particles transforms from solid entities to waves of potential, constantly in flux. Instead of envisioning particles as tiny, discrete points, we now embrace a view that sees them as fluid manifestations of probability. This shift challenges our classical intuitions and compels us to rethink the very essence of reality. The interplay between observer and observed not only reshapes our understanding of physical phenomena, but also invites us to reflect on the nature of consciousness itself. Are we merely passive spectators in this cosmic theater, or do our thoughts and intentions play a role in the unfolding narrative? The philosopher Erwin Schrödinger, known for his thought experiment involving a cat that is simultaneously alive and dead, encourages us to ponder the implications of observation on our reality. As we delve into these profound questions, we begin to appreciate the beauty of uncertainty that pervades the quantum realm. The fluidity of existence, the dance of probabilities, and the interconnectedness of all things create a rich tapestry of meaning. In embracing the unknown, we open ourselves to a deeper understanding of our place within the cosmos. The philosophical implications of quantum mechanics extend beyond the confines of science, inviting us to explore the essence of existence itself. As we navigate this intricate landscape of thought, we are reminded that the journey through quantum mechanics is not merely an intellectual pursuit. It is a profound exploration of the nature of reality, consciousness, and the very fabric of our being. In this vast ocean of uncertainty, we may find solace in the idea that we are not alone in our quest for understanding. The great minds of history, from Bohr to Everett, have grappled with these questions, each contributing to the ever-evolving narrative of science and philosophy. As we continue our exploration, let us remain open to the profound insights that quantum mechanics offers, embracing the complexity and beauty that lies within the mysteries of existence. As we contemplate the ramifications of the uncertainty principle, we are drawn into a deeper understanding of how these principles challenge classical physics and reshape our worldview. The uncertainty that permeates the quantum landscape suggests that the very act of observation alters the properties of particles, leading us to question the solidity of an objective reality. What does it mean for our understanding of the universe if the act of knowing changes what is known? This inquiry leads us to consider the implications for our day-to-day lives. Imagine for a moment that every choice you make not only influences your own path, but also ripples through the fabric of reality, creating branches of existence with each decision. This notion echoes the musings of physicist Richard Feynman, who once said, "The imagination of nature is far greater than the imagination of man." The universe is a complex interplay of infinite possibilities, and our role as observers and participants in this cosmic dance is both humbling and awe-inspiring. The philosophical implications extend into questions of existence and identity. If every quantum event spawns a multitude of realities, how do we define ourselves within this vast multiverse? The many worlds interpretation encourages us to visualize our lives as a series of threads woven into an intricate fabric, each choice giving rise to a new narrative. Are we defined by the paths we take or by the possibilities we leave behind? As we navigate through these profound questions, we find ourselves revisiting the observer effect. The nature of measurement in quantum mechanics is not merely a technical issue. It invites us to reflect on our consciousness and its role in shaping reality. When we observe a quantum system, we are not just passive witnesses. We actively engage with the universe, influencing its unfolding. This interaction evokes a sense of unity, suggesting that we are not separate from the cosmos, but rather integral to its intricate design. Consider the implications of this unity on our understanding of free will. If our choices can influence quantum events, does this suggest a greater agency in shaping our reality? The philosopher and physicist David Bohm posited a holistic view of the universe, where the observer and the observed are inextricably linked. In this view, our consciousness is not merely an isolated phenomenon, but a vital part of the cosmic whole, engaged in a continuous dialogue with existence itself. The uncertainty principle challenges the notion of an absolute reality, suggesting that our understanding is inherently tied to the act of observation. This invites us to embrace uncertainty not as a limitation, but as an opportunity for exploration and wonder. The universe, in all its complexity, is not a static entity, but a dynamic tapestry of interactions, where each moment holds the potential for new discoveries and insights. In the quiet contemplation of these ideas, we might find ourselves reflecting on the nature of truth itself. Is truth a fixed destination, or is it a journey that evolves with our understanding? The interplay of quantum mechanics and philosophy encourages us to remain open to the myriad possibilities that life presents. Just as particles exist in a state of potential, so too do our thoughts and intentions shape the unfolding narrative of our lives. As we continue to explore the philosophical implications of quantum mechanics, we are reminded that the journey is as important as the destination. The questions we ask and the insights we gain illuminate our path, guiding us through the intricate web of existence. Embracing uncertainty allows us to cultivate a deeper appreciation for the interconnectedness of all things, inviting us to engage with the universe in a meaningful way. In this delicate balance between determinism and indeterminism, we discover a profound truth. The universe is a symphony of possibilities, and each of us plays a vital role in its harmonious composition. As we venture further into the realms of quantum mechanics and its philosophical implications, let us remain curious, open-hearted, and ready to embrace the mysteries that lie ahead. Chapter 4. Experimental evidence supporting the principle. The realm of quantum mechanics is rich with experimental evidence that illuminates the principles we have begun to explore. One of the most celebrated demonstrations of the uncertainty principle can be traced back to landmark experiments that have shaped our understanding of the quantum world. These experiments serve as a bridge between abstract theory and tangible reality, allowing us to glimpse the whimsical nature of particles at their most fundamental level. Consider the double-slit experiment, a cornerstone in the study of wave-particle duality. Imagine a beam of light or a stream of particles, such as electrons, directed at a barrier with two narrow slits. On the other side of the barrier, a screen awaits to capture the impacts. When we observe the particles traveling through the slits, we witness a surprising phenomenon. They create an interference pattern, a hallmark of waves. This pattern suggests that each particle behaves as if it passes through both slits simultaneously, interfering with itself. Yet, when we set up a measurement apparatus to determine which slit the particle goes through, the interference pattern disappears, and we see distinct impacts on the screen, as if the particles have chosen a singular path. This experiment evokes a sense of wonder. How can particles embody both wave-like and particle-like characteristics? As physicist Richard Feynman expressed, the only thing that can be said is that if you want to understand quantum mechanics, you have to accept that it is fundamentally strange. This strangeness reveals the heart of the uncertainty principle, where the act of measurement itself alters the state of what we observe. As we seek to clarify the path of a particle, we inevitably obscure other vital information, such as its momentum. Moving deeper into the quantum landscape, we encounter the phenomenon of quantum entanglement, which further elucidates the limits of measurement. Picture two particles that become entangled, their properties intertwined in a manner that transcends distance. When we measure one particle, we instantly gain knowledge about the other, regardless of how far apart they are. This instantaneous link defies our classical understanding of communication and causality. Albert Einstein famously referred to this as spooky action at a distance, highlighting the bewildering implications of such connections. Entanglement challenges the very notion of separability in quantum systems. Imagine a pair of dancers, perfectly synchronized, moving in harmony no matter the distance between them. When one dancer spins, the other mirrors the motion, regardless of how far apart they are. This interconnectedness hints at a deeper reality, where measurement is not merely an active observation, but rather an intricate interplay of relationships that binds particles together. The implications of entanglement extend beyond theoretical musings. Advances in technology have begun to demonstrate the practical manifestations of uncertainty. Quantum computing, for instance, harnesses the principles of superposition and entanglement to perform calculations at speeds unimaginable with classical computers. In this realm, qubits can exist in multiple states at once, allowing complex computations to unfold simultaneously. The uncertainty inherent in these states does not hinder progress. Instead, it propels technological innovation into uncharted territories. Furthermore, the field of quantum cryptography has emerged, leveraging the principles of uncertainty to create secure communication channels. Imagine sending a message protected by the laws of quantum mechanics, where any attempt to eavesdrop disturbs the system, alerting the sender and receiver to the presence of an intruder. This remarkable application of the uncertainty principle not only protects information, but also showcases how uncertainty can be a tool for enhancing security in our increasingly digital world. As we explore these experimental findings, we must ask ourselves, what does this mean for our understanding of reality? The uncertainty principle is not merely an abstract notion confined to the pages of textbooks. It is an essential part of the very fabric of the universe. Each experiment and technological advancement adds to a growing narrative, one that invites us to reconsider our perceptions of certainty and measurement. In reflecting upon the landscape of quantum mechanics, we find ourselves at a crossroads of knowledge and mystery. The experimental evidence supporting the uncertainty principle unfurls like a tapestry, rich with insights and implications. The double-slit experiment, the enigma of quantum entanglement, and the technological marvels born from these principles all serve to amplify the significance of uncertainty in our understanding of the universe. The journey through these experiments reveals not only the limitations imposed by measurement, but also the vast potential that lies within uncertainty. As we stand before the infinite possibilities that quantum mechanics offers, we are reminded of the words of physicist Max Planck, who stated, "When you change the way you look at things, the things you look at change." This shift in perspective encourages us to embrace the unknown and to find beauty in the complexity of the world around us. In the quiet moments of contemplation, consider the particles that weave the very essence of existence. Each one carries with it a story of uncertainty, a whisper of the delicate balance between possibility and reality. What role do we play in this intricate dance of measurement and observation? As we continue to explore the depths of quantum mechanics, we find ourselves not just as passive observers, but as active participants in the unfolding narrative of the cosmos. With each experiment, we peel back the layers of understanding, revealing the profound connections that bind us to the universe. The uncertainty principle, with its far-reaching implications, invites us to step into a world where certainty is an illusion and wonder reigns supreme. As we delve into the experimental evidence, we discover that the journey through uncertainty is not one to be feared, but rather embraced as we seek to understand the nature of reality itself. As we immerse ourselves in the world of experimental evidence, we find ourselves drawn to yet another fascinating aspect of quantum mechanics, the intricate relationship between quantum entanglement and the very act of measurement. The phenomenon of entanglement is not merely a curious oddity. It serves as a profound demonstration of the limits imposed by our understanding and the implications of the uncertainty principle. To visualize entanglement, imagine two particles generated in a single event, their fates intertwined like a pair of celestial dancers. These particles share a connection that persists regardless of the distance that separates them. When one particle is measured, its state is instantly determined, and at that moment, the state of the other particle is defined as well, even if it exists light years away. This curious nature compels us to consider, what does it mean for information to travel faster than light? The answer lies in the very fabric of quantum mechanics, where concepts like locality and separability blur and redefine our conventional understanding. The implications of this phenomenon echo through the corridors of physics. Nobel laureate Alain Aspect conducted groundbreaking experiments that tested the nature of entangled particles, revealing the inherent unpredictability in their behavior. Imagine a game where the rules change based on observation. This is the essence of quantum entanglement. It challenges our perceptions and compels us to confront the limitations of classical physics. The relationship between measurement and uncertainty is not confined to theoretical musings. As technology advances, we see practical applications that highlight the significance of these principles. Quantum technologies such as quantum communication and quantum teleportation harness the power of entanglement. Picture a world where secure communication relies on the very uncertainty that perplexes us. Attempts to intercept quantum information will inevitably alter the state of the system, alerting the sender and receiver to potential breaches. This is not merely a safeguard. It is a testament to the beauty and utility of uncertainty. As these advancements unfold, we may wonder how they reshape our understanding of reality. The uncertainty principle, as revealed through entanglement and measurement, prompts us to question the nature of existence itself. If particles can be so intimately connected across vast distances, what does that say about our interconnectedness in the universe? Each measurement, each interaction reverberates through the fabric of reality, illustrating that we are part of a much larger cosmic dance. Exploring the practical advancements in technology further illuminates how uncertainty manifests in our everyday lives. Quantum sensors, for instance, leverage the principles of uncertainty to achieve unprecedented levels of precision. Imagine a device so sensitive that it can detect minute changes in gravitational fields, providing insights into everything from geological formations to the movement of planets. These sensors capitalize on the inherent uncertainty of quantum states, allowing us to perceive the world in ways previously beyond our grasp. The development of quantum computing stands as a testament to the power of harnessing uncertainty. In the world of classical computing, bits operate in a binary fashion, representing either a 0 or a 1. Quantum computers, however, utilize qubits, which can exist in superpositions of both states simultaneously. This remarkable capability allows quantum computers to solve complex problems at speeds unattainable by their classical counterparts. As we ponder these advancements, we might ask ourselves, how might our understanding of computation evolve when we embrace the uncertainty encoded within quantum systems? In this light, uncertainty is not merely a hindrance, it becomes a wellspring of innovation. The ability to explore multiple possibilities at once opens doors to new realms of inquiry and understanding. With each technological leap, we find ourselves not just observers of quantum phenomena, but active participants in the unfolding narrative of scientific discovery. As we reflect on the tapestry of experimental evidence supporting the uncertainty principle, we are reminded of the words of physicist Niels Bohr. We are not only observers, we are participants in the phenomena we study. This perspective invites us to consider our role within the quantum world, where our observations shape reality in ways we are only beginning to understand. The beauty of quantum mechanics lies in its capacity to challenge, to provoke thought, and to inspire wonder. The interplay between measurement and uncertainty reveals a symbiotic relationship that transcends mere observation, inviting us to engage more deeply with the mysteries of existence. It is a gentle reminder that in the pursuit of knowledge, uncertainty is not an enemy, but a companion, guiding us toward profound insights. As we continue to explore the implications of these experimental findings, we find ourselves standing at the threshold of discovery, where the boundaries of understanding blur and new horizons emerge. The journey through uncertainty beckons us forward, urging us to embrace the complexities of the quantum world and the rich possibilities that lie within. Each experiment, each technological innovation, serves as a testament to the profound connections that bind us to the universe, inviting us to reflect on our place within this intricate web of existence. As we continue our exploration of experimental evidence supporting the uncertainty principle, we encounter the intersection of technology and quantum mechanics. This intersection has not only enhanced our understanding of uncertainty, but has also paved the way for remarkable advancements in various fields. One striking example is the emergence of quantum sensors, which utilize the very principles of uncertainty to achieve unprecedented levels of sensitivity and precision. Imagine a device capable of detecting the faintest gravitational waves rippling through the fabric of space-time. These sensors exploit the delicate balance of quantum states, allowing them to measure phenomena that were once thought to be beyond our reach. The application of such technology extends to various domains, from medical imaging to geophysical exploration, revealing insights that can transform our understanding of the world around us. In the realm of quantum communication, the implications of the uncertainty principle manifest in profound ways. Quantum key distribution, a method of secure communication, relies on the inherent uncertainty of quantum states to ensure that any attempt at eavesdropping will alter the information being transmitted. Visualize a secure conversation where the mere act of someone trying to listen in would disrupt the message, alerting both the sender and receiver. This fascinating interplay between uncertainty and information security not only illustrates the practical applications of quantum mechanics, but also highlights the concept of measurement's impact on reality. The potential of quantum computing brings another layer of intrigue to our journey. Quantum computers, with their ability to harness superposition and entanglement, shift the paradigms of computation. Picture a machine that can analyze vast amounts of data simultaneously, processing information in ways that classical computers cannot fathom. This transformative capability arises from the uncertainty that allows qubits to exist in multiple states at once. The exploration of this technology is akin to unlocking a treasure chest of possibilities, where traditional computing limitations become a thing of the past, giving rise to solutions for complex problems in fields ranging from cryptography to drug discovery. As we reflect on these advancements, it is essential to ponder the broader implications of uncertainty in our understanding of the universe. What does it mean for our perception of reality when the act of measurement can influence the very state of a particle? The journey through quantum mechanics invites us to reconsider our relationship with knowledge itself. Are we mere observers in a world governed by certainty, or are we participants in a dynamic interplay of potentialities? This contemplation echoes the sentiments of physicist Erwin Schrödinger, who famously illustrated the concept of superposition with his thought experiment involving a cat that is simultaneously alive and dead until observed. This paradox not only challenges our intuitive understanding of existence, but also emphasizes the significance of observation in the quantum realm. The act of measurement becomes a pivotal moment, where possibilities collapse into a single reality, reminding us that uncertainty is not an obstacle, but rather a pathway to deeper insights. The experiments that underpin the uncertainty principle serve as a testament to the intricate dance between measurement and reality. As we delve into this dance, we uncover layers of complexity that challenge our perceptions and prompt us to embrace the unknown. Each technological advancement inspired by quantum principles reaffirms the notion that uncertainty is woven into the very fabric of existence, inviting us to explore further. As we stand at the confluence of theory and practice, we are compelled to ask ourselves, how can we leverage the power of uncertainty to enhance our understanding of the universe? The journey through quantum mechanics is not merely an academic pursuit. It is a quest to uncover the mysteries that govern our reality. In this exploration, we find not only answers, but also a wealth of questions that beckon us forward, urging us to embrace the enigma of the quantum world. In this space of inquiry, we are reminded of the words of physicist David Bohm, who articulated the interconnectedness of all things. The universe is not a collection of separate parts, but a single whole. This perspective resonates deeply with the findings of quantum mechanics, where entangled particles reveal a profound interconnectedness that transcends distance and time. As we unravel the threads of uncertainty, we begin to see the universe as a cohesive entity, where every element is linked in an intricate web of relationships. As we navigate this wondrous landscape, let us remain open to the possibilities that uncertainty brings. Each experimental finding, each technological advancement, illuminates the path ahead, guiding us toward a more profound understanding of our place in the cosmos. The uncertainty principle, in all its complexities, invites us to embrace the journey of discovery, where the beauty of the unknown enriches our quest for knowledge and sparks our imagination. In this journey, we come to appreciate that uncertainty is not something to be feared, but rather a source of inspiration. It beckons us to explore, to question, and to marvel at the intricate dance of particles that compose our universe. Each experiment stands as a testament to the resilience of human curiosity, reminding us that in our pursuit of knowledge, we are not merely observers of the cosmos, but integral participants in its unfolding story. As we press onward, we find ourselves at the threshold of new discoveries, where the interplay of uncertainty and measurement continues to shape our understanding of the fundamental nature of reality. Each step we take in this exploration brings us closer to unraveling the mysteries that lie within, inviting us to embrace the complexities of existence with open hearts and inquisitive minds. Chapter 5. The Role of Quantum States and Wave Functions. In the vast and intricate landscape of quantum mechanics, wave functions emerge as essential companions in our quest to understand the nature of particles. Imagine a gentle ripple across a serene lake, where each wave conveys information about the presence and behavior of particles, much like the wave functions that describe them. These mathematical entities encapsulate the probabilities of finding a particle in various states, illuminating the profound uncertainty that permeates the quantum realm. Wave functions serve as the very heart of quantum mechanics, offering insight into the potential properties of particles. They are not mere abstractions, but vivid representations of what could be, a tapestry of possibilities woven together by the threads of quantum states. Each wave function contains valuable information, allowing physicists to predict the likelihood of certain outcomes, yet it does so with an inherent uncertainty. This uncertainty is beautifully illustrated in how wave functions depict the dual nature of particles, behaving both as particles and waves, depending on how they are measured. Consider the concept of uncertainty, which we explored in previous chapters. Just as the uncertainty principle reveals the limitations of measuring position and momentum, wave functions embody this principle in a more profound way. They express not just the potential locations of particles, but also the myriad paths they might take. Picture a foggy path where the destination is obscured. You can sense where you might be headed, but cannot pinpoint your exact location. Similarly, wave functions illustrate the uncertainty in particle properties, providing a range of probabilities rather than certainties. When we delve deeper into the nature of wave functions, we encounter the phenomenon of wave function collapse. This process occurs upon measurement and is akin to a spotlight shining on a stage, illuminating a single actor while the rest remain shrouded in darkness. Until we make an observation, particles exist in a superposition of states, embodying multiple possibilities at once. However, the moment we measure a particle, its wave function collapses, and it assumes a definite state. This transformation raises intriguing questions about reality and observation. What does it mean for an outcome to exist only once we observe it? The collapse of the wave function challenges our traditional notions of existence. In the words of physicist Eugene Wigner, the laws of quantum mechanics describe the behavior of systems that are not well defined until they are observed. This idea resonates deeply within the philosophical implications of quantum mechanics. It suggests that our act of measuring is not merely a passive observation, but an active engagement that shapes the reality we perceive. As we ponder the implications of wave function collapse, we also encounter its effects on predicting particle behavior. The predictions offered by wave functions are not deterministic as in classical mechanics. Instead, they provide a probabilistic framework, where outcomes are not guaranteed, but rather weighted by likelihood. Imagine a game of chance, where the dice are rolled, and while you can predict the potential outcomes, the specific result remains uncertain. Wave functions allow physicists to calculate probabilities, offering insights into how particles might behave under various conditions, yet they can never provide absolute certainty. This probabilistic nature is further exemplified in experiments like the double-slit experiment, which we touched upon in earlier chapters. When particles are not observed, they exhibit wave-like behavior, creating interference patterns that speak to their dual nature. However, the moment we intervene with a measurement, this wave function collapses, resulting in particles behaving like distinct entities rather than waves of possibility. What does this reveal about the relationship between observation and reality? The role of wave functions extends beyond mere theoretical constructs. They have practical implications in the realm of quantum technologies. Quantum computing, for instance, harnesses the power of superposition and entanglement, relying on wave functions to process information in ways that classical computers cannot. This emerging field holds the promise of revolutionizing our computational capabilities, driven by the very principles that govern wave functions and their uncertainties. Imagine a world where complex problems can be solved in mere moments, where the intricacies of cryptography and data analyses are handled with effortless grace. This is the potential unlocked by understanding and harnessing quantum states and wave functions. As we continue to explore this fascinating domain, we find ourselves standing at the threshold of a new era, where the very fabric of reality is interwoven with probabilities and possibilities. The journey through the quantum realm invites us to embrace uncertainty as a fundamental aspect of existence. Wave functions remind us that the universe is not a rigid machine, but a fluid and dynamic tapestry of interactions, where every observation reshapes the landscape. As we move forward, let us carry this understanding with us, recognizing that the mysteries of quantum mechanics, much like the cosmos itself, are not meant to be fully deciphered, but rather experienced with wonder and curiosity. In this dance of particles and waves, we find not only the essence of quantum mechanics, but also a reflection of our own experiences. Just as wave functions embody uncertainty, our lives are woven with moments of unpredictability and possibility. Each choice we make, each path we take, is a step into the unknown, where outcomes are not guaranteed, but filled with potential. As we contemplate the significance of wave functions and their role in quantum mechanics, we are reminded of the profound interconnectedness of all things. The particles that make up our universe, the very fabric of reality, are bound by the same principles that govern the quantum world. This realization invites us to explore not only the physical realm, but also the philosophical questions that arise from our understanding of existence itself. What does it mean to truly know something? Can we ever grasp the entirety of reality, or are we destined to remain explorers in a vast ocean of uncertainty? These questions echo through the corridors of quantum thought, urging us to seek deeper understanding while embracing the beauty of the unknown. As we reflect on the wave functions and their implications, let us remain open to the intricacies of the quantum world, where uncertainty reigns, yet offers boundless opportunities for discovery. The dance of particles, the collapse of wave functions, and the probabilities that shape our universe are all part of a grand symphony, resonating with the mysteries of existence. In this realm, the boundaries between observer and observed blur, inviting us to consider our role in the unfolding narrative of the cosmos. As we stand on the precipice of understanding, let us take a moment to breathe deeply, allowing the soothing currents of possibility to wash over us. In this journey through quantum states and wave functions, we find not only a scientific exploration, but also a personal reflection on the nature of reality itself. What lies ahead in our exploration of quantum mechanics? How do wave functions continue to shape our understanding? And what new revelations await us as we delve deeper into this extraordinary realm? As we explore the implications of predicting particle behavior through wave functions, we enter a landscape where the boundaries of certainty blur and possibilities unfold in unexpected ways. The probabilistic nature of quantum mechanics invites us to challenge our classical intuitions. Unlike the deterministic predictions of classical physics, where a well-defined initial state leads to predictable outcomes, quantum mechanics reveals a world enriched by probabilities. Imagine standing at the edge of a vast forest where each path diverges into countless trails. Each trail represents a different potential outcome, shaped by the wave function's probabilities. This is the essence of quantum prediction, a multitude of possibilities that coexist until we make a choice or take an action. The very act of measurement, as we have previously discussed, transforms this complex web of probabilities into a single observable reality. One cannot help but ponder the role of the observer in this delicate interplay. In the words of physicist Wolfgang Pauli, we cannot be sure that the world is as it is when we do not observe it. This perspective is not merely a poetic musing, but an invitation to reflect on the relationship between consciousness and reality. What does it mean for a particle to exist in a state of potentiality, awaiting an observation to crystallize its fate? The very act of observing seems to bestow a certain definition upon the particle, collapsing its wave function into a specific state. Throughout history, many brilliant minds have grappled with these profound questions. Niels Bohr, a pivotal figure in the development of quantum mechanics, embraced the idea that the universe operates on principles that defy classical logic. He once remarked, "If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet." This shock comes from confronting the realization that our observations are intertwined with the fabric of reality itself, leading us to reconsider our role as participants in the unfolding story of the universe. The implications of wave functions extend far beyond theoretical musings. They have tangible applications in modern science and technology. Quantum mechanics underpins advancements in fields such as quantum computing, where the principles of superposition and entanglement enable unprecedented computational power. Imagine a computer that can process vast amounts of information simultaneously, solving complex problems that would take classical computers an eternity to crack. This is not a distant dream, but a burgeoning reality, propelled by our understanding of quantum states and wave functions. As we journey through the implications of wave functions in predicting particle behavior, we encounter the notion of quantum entanglement. Picture two particles, intimately linked regardless of the distance that separates them. When a measurement is performed on one particle, its partner instantaneously reflects a corresponding change, as if they are communicating across the void. This phenomenon challenges our classical notions of locality and causality, suggesting that information can be shared instantaneously, transcending the limitations of space and time. Quantum entanglement has profound implications for the way we understand the universe. Albert Einstein famously referred to it as spooky action at a distance, highlighting the perplexing nature of this connection. As we delve deeper into the fabric of reality, we are confronted with a powerful question. What does it mean for particles to be connected in such a fundamental way? Could it be that the universe is a vast web of interconnectedness, where the boundaries between individual entities are merely an illusion? The exploration of wave functions and their implications for predicting particle behavior leads us to a deeper understanding of the nature of reality. It teaches us that certainty is not an inherent quality of the universe, but rather a construct of our observations. Like a painter who shapes a canvas with each brushstroke, we contribute to the unfolding narrative of existence with our measurements and interactions. In this landscape of quantum possibilities, we are reminded of the beauty of uncertainty. Embracing the unknown allows us to explore the depths of reality with an open heart and mind. Just as a river flows freely, carving its path through the earth, we too can navigate the currents of possibility, trusting in the journey rather than fixating on the destination. As we reflect on the role of wave functions and their significance in quantum mechanics, we recognize that our quest for understanding is not merely about uncovering the hidden truths of the universe. It is also about embracing the wonder and mystery that surround us. The interplay between observation and reality invites us to cultivate a sense of curiosity, to marvel at the intricate dance of particles, and to revel in the endless possibilities that lie ahead. What future revelations await us as we continue to explore the depths of quantum mechanics? How will our understanding of wave functions shape the trajectory of scientific inquiry and philosophy alike? These questions beckon us to venture forward, guided by the light of curiosity and the promise of discovery. Each step we take in this remarkable journey reveals new layers of complexity, inviting us to engage with the universe in ways we have yet to imagine. As we prepare to delve deeper into the mysteries of quantum mechanics, let us carry with us the insights we have gained so far, allowing them to inform our exploration of what lies ahead. The principles that govern quantum states and wave functions are not merely abstract concepts, but vibrant threads woven into the fabric of our reality. In this grand tapestry, we find not only scientific understanding, but also a profound reflection on the nature of existence itself. What new dimensions of knowledge await us as we continue to engage with the quantum world? How might our evolving understanding of wave functions influence our perception of reality? As we ponder these questions, we open ourselves to the beauty of exploration, ready to embrace the unfolding narrative of the cosmos. Chapter 6. The Uncertainty Principle in Technology. In the vibrant tapestry of modern technology, the uncertainty principle serves as a guiding light, illuminating pathways that were once deemed impossible. Its implications stretch far beyond the confines of theoretical physics, finding applications that are reshaping our world in profound ways. Imagine the ripple of a pebble dropped into a still pond, where each wave represents a new possibility, a new technology born from the enigmatic dance of particles at the quantum level. One of the most striking applications of the uncertainty principle can be found in the realm of quantum computing. This innovative technology harnesses the very essence of uncertainty to deliver computational power that surpasses anything classical computers can achieve. As we consider the limitations of traditional computing, we find that they operate on bits, the simplest units of information, locked in a binary state of either 0 or 1. In contrast, quantum computers leverage qubits, which can exist in multiple states simultaneously thanks to the principle of superposition. Imagine a qubit as a spinning coin, where it embodies both heads and tails at once until it is measured. This unique property allows quantum computers to explore numerous solutions to a problem in parallel, exponentially increasing their efficiency. As we ponder this remarkable capability, one might wonder, how does uncertainty contribute to this computational prowess? The answer lies in the very nature of quantum mechanics, where the probabilities dictated by the uncertainty principle allow quantum systems to exist in states that classical systems simply cannot. The implications of quantum computing extend far beyond the speed of calculations. They promise to revolutionize fields such as cryptography, optimization, and complex modeling. The excitement surrounding quantum computing is palpable, with pioneers like Richard Feynman recognizing its potential. He once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." This playful yet profound assertion underscores the transformative nature of this field, encouraging us to embrace the unknown as we venture into uncharted territories of technology. As we explore these avenues, we encounter quantum cryptography, a field that elevates security measures to unprecedented heights. Traditional cryptographic methods rely on the computational difficulty of certain mathematical problems, but quantum cryptography takes a different approach, utilizing the principles of quantum mechanics to ensure secure communication. At the heart of quantum cryptography is a technique known as quantum key distribution, or QKD. This method allows two parties to generate a shared, secret key through the exchange of quantum bits, or qubits, over a distance. The beauty of this system lies in the uncertainty principle itself. Any attempt to eavesdrop on the communication will introduce detectable disturbances in the qubits. Imagine a sentinel watching over a fragile flower, where the mere act of peering disrupts its delicate beauty. In the same way, The act of measurement in quantum systems reveals the presence of an intruder, ensuring that the integrity of the communication remains intact. The implications of quantum cryptography are profound. It offers a level of security that is theoretically unbreakable, bound only by the laws of physics, rather than the capabilities of computational power. As we embrace this technology, we might envision a future where our personal data and communications are safeguarded by the very fabric of the universe, an unyielding barrier against prying eyes. Alongside these advancements, we find measurement devices that utilize quantum principles to enhance our understanding of the world around us. These devices, often referred to as quantum sensors, exploit the delicate interplay between particles and waves to achieve unprecedented precision in measurements. Consider gravitational wave detectors, which rely on the principles of quantum mechanics to detect ripples in spacetime caused by cosmic events, such as colliding black holes. Imagine standing on a tranquil shore, listening to the gentle lapping of waves, only to realize that these waves carry messages from the farthest reaches of the universe. Quantum sensors, through their extraordinary sensitivity, allow us to perceive these faint echoes of celestial phenomena. Translating them into meaningful data, they open a window into the cosmos, revealing insights that were once beyond our grasp. The development of these technologies is spearheaded by brilliant minds in the field. Scientists like Anton Zeilinger, a pioneer in quantum information science, have dedicated their careers to exploring the profound implications of quantum mechanics. Zeilinger once stated, "The world is not as it seems." His words resonate deeply as we consider the transformative impact of the uncertainty principle on technology. In addition to gravitational wave detection, quantum sensors are making waves in fields such as medicine, where they are used to enhance imaging techniques. By leveraging the principles of quantum mechanics, researchers have developed imaging systems that can detect minuscule changes in cellular structures, offering new avenues for early disease diagnosis and treatment. The potential is staggering as we draw closer to a future where diseases can be detected at their inception, allowing for timely intervention. As we explore these remarkable applications of the uncertainty principle, we are reminded of the interconnectedness of technology and the fundamental laws of nature. Every advancement, every innovation, is a testament to our ability to harness uncertainty, transforming it into a tool for understanding and creation. Yet amid this whirlwind of progress, we must pause and reflect. What does it mean to embrace uncertainty in our technological pursuits? As we stand on the precipice of a new era, one where quantum mechanics shapes our reality, we are confronted with both possibilities and challenges. The very essence of uncertainty invites us to question, to explore, and to innovate in ways we have yet to imagine. In this unfolding narrative, the uncertainty principle is not merely a scientific concept, it becomes a philosophical lens through which we view our world. It invites us to accept that knowledge is not static but ever-evolving, much like the quantum states that define the particles around us. As we integrate these principles into our lives, we may find comfort in the knowledge that uncertainty is not our enemy, but rather a companion on this journey of discovery. Each step we take into the unknown is an act of courage, a testament to our innate curiosity and the desire to understand the universe in which we live. In every application of the uncertainty principle, from quantum computing to cryptography and measurement devices, we see a reflection of our quest for knowledge. Each innovation is like a beacon, guiding us toward a deeper understanding of the cosmos and our place within it. As we continue to embrace this journey, we can anticipate a future rich with possibilities, where uncertainty becomes a source of inspiration and wonder. In the soft embrace of these ideas, we find a sense of peace, a reminder that even in uncertainty, there is beauty. The journey ahead promises to be filled with discoveries that will challenge our perceptions and deepen our connection to the universe. With each advancement, each insight, we step closer to unveiling the mysteries that lie within the fabric of reality itself. The unfolding narrative of quantum technology does not merely end with quantum sensors and cryptography. It extends into the heart of innovation itself, quantum computing's ambitious quest to redefine our understanding of computation. Building upon the unique principles of uncertainty, these machines are set to revolutionize how we process information. Imagine a world where complex problems, once thought insurmountable, can be tackled in mere moments, thanks to the inherently probabilistic nature of quantum mechanics. At the core of quantum computing lies a concept known as entanglement, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. This baffling principle allows qubits to become intertwined, such that the state of one qubit is directly linked to the state of another, regardless of the distance separating them. It is as if they form an invisible thread, binding them together in a shared reality. This interconnectedness is pivotal for enhancing computational power, as entangled qubits can collectively process vast amounts of information simultaneously. Consider the implications of entangled qubits in a computational task. If you visualize a vast library, each qubit represents a book filled with information. Traditional computers would sift through one book at a time, while a quantum computer, leveraging entanglement, could explore numerous books simultaneously. This parallel processing capability opens the door to solving intricate problems in fields such as materials, science, drug discovery, and complex system modeling, where the solutions reside within a labyrinth of possibilities. As we delve into the realm of quantum computing, the contributions of pioneers in the field illuminate our path. Figures like David Deutsch have postulated that quantum computers can simulate any physical system, a notion that defies the classical limits of computation. Deutsch's assertion embodies the spirit of exploration that drives researchers today. He proclaimed, "The universe is not a machine, it is a computer," suggesting that the fundamental nature of reality itself mirrors the workings of quantum computation. Yet the journey toward practical quantum computing is fraught with challenges. The delicate nature of qubits makes them susceptible to decoherence, a phenomenon where they lose their quantum state due to interactions with their environment. This fragility raises questions about the stability and scalability of quantum systems. How do we harness the power of uncertainty without succumbing to its chaotic tendencies? Researchers are exploring various strategies to mitigate decoherence, such as employing error-correcting codes and developing quantum algorithms that are inherently resistant to noise. These efforts aim to create robust quantum systems capable of maintaining coherence long enough to perform meaningful computations. Each breakthrough in this domain not only holds promise for technological advancement, but also deepens our understanding of the underlying principles of quantum mechanics. As we reflect on the broader implications of these advancements, it becomes clear that quantum technologies are not merely tools for computation or security. They represent a paradigm shift in how we perceive information and its relationship to the universe. The uncertainty principle, once seen as a limitation, now emerges as a catalyst for innovation, inviting us to rethink our assumptions about certainty, predictability, and control. In the context of quantum cryptography, the lessons of uncertainty serve to fortify our communications against the threats of an increasingly digital world. As data breaches become more prevalent, the promise of quantum-secured systems offers a glimmer of hope. Imagine a future where your most sensitive information is safeguarded not just by complex algorithms, but by the very laws of nature. This is not a distant dream. It is a reality being forged in laboratories across the globe. Moreover, the implications of quantum technologies extend to the realm of artificial intelligence and machine learning. By integrating quantum computing with AI, we can enhance the processing capabilities necessary for vast datasets, unlocking new avenues for discovery and insight. Picture an AI that not only learns from data but can also explore the probabilistic nature of uncertainty to make predictions. This fusion of disciplines could lead to breakthroughs in understanding complex systems, from climate modeling to personalized medicine. As we stand on the cusp of this technological renaissance, we are reminded of the words of physicist Niels Bohr, who encouraged us to embrace the mysterious. The opposite of a fact is falsehood, but the opposite of a profound truth may well be another profound truth. This sentiment resonates deeply within the quantum realm, where uncertainty fosters not just innovation, but also humility in our quest for knowledge. In this evolving landscape, the uncertainty principle continues to guide us, not as a barrier, but as a bridge to a future rich with possibilities. Each step into the quantum realm is a journey into the unknown, filled with challenges and discoveries that stretch the fabric of our understanding. As we embrace this uncertainty, we cultivate a mindset that values exploration over certainty, curiosity over complacency. In the gentle embrace of these ideas, we find a soothing rhythm that invites us to reflect on our relationship with technology. Our tools, shaped by the principles of quantum mechanics, are extensions of our desire to comprehend the universe, an expression of our innate curiosity and drive to connect with the unknown. Just as the tides ebb and flow, so too does our understanding shift, revealing deeper truths hidden beneath the surface. With each advancement in quantum technology, we inch closer to unveiling the mysteries of existence, guided by the shimmering light of uncertainty. It is a journey that challenges us to reimagine our place in the cosmos, to embrace the unknown as a vital part of our human experience. The future beckons, inviting us to explore the realms where uncertainty flourishes, and in doing so, we may discover the beauty that lies within the very fabric of reality itself. Chapter 7. The Uncertainty Principle and Thermodynamics. The dance of particles within the quantum realm is governed by principles that often seem at odds with our classical intuitions. Among these principles, the uncertainty principle stands out, weaving its intricate threads through the fabric of thermodynamics. This connection between quantum uncertainty and thermodynamic principles invites us to explore the very nature of energy and the role of entropy. At the heart of thermodynamics lies the concept of energy states, which can be imagined as the many rooms in a vast mansion. Each room represents a different state of energy, filled with potential yet distinctly separate. The uncertainty principle asserts that as we attempt to pin down a particle's position within this mansion, we inevitably introduce uncertainty into our knowledge of its momentum. This interplay between position and momentum extends into thermodynamic systems, where energy states are defined not just by what is known, but by what cannot be known with absolute certainty. Picture a warm cup of tea resting on a table, steam rising gently into the air. The energy within that cup is continually transferring to the surrounding environment, a process influenced by the uncertainty of particle interactions. The more we understand about the energy state of the tea, the less we can assert about the precise behavior of the molecules as they collide and exchange energy with their surroundings. This uncertainty plays a crucial role in entropy, the measure of disorder in a system. As particles vibrate and move, their energy states fluctuate, leading to a gradual increase in entropy or disorder within the system. Imagine a room filled with balloons. As they bounce against one another in an unpredictable fashion, the arrangement becomes increasingly chaotic, mirroring the rise in entropy. The very act of measuring an energy state, much like attempting to control the movement of those balloons, introduces a layer of uncertainty. We can calculate probabilities of where the particles will be at any given moment, but exact predictions escape us. The implications of this uncertainty extend to our understanding of heat. Heat, a form of energy transfer, arises from particle interactions at the atomic level. When we speak of heat in thermodynamic terms, we reference the collective energy states of a multitude of particles. The uncertainty principle introduces a fascinating twist to this narrative. It suggests that as we measure the temperature of a substance, an indication of the average kinetic energy of its particles, we are, in essence, tapping into a world of inherent unpredictability. Consider the words of physicist Richard Feynman, who once remarked, "The laws of quantum mechanics tell us that we cannot exactly predict the future." This realization invites us to reconsider how we approach thermodynamic systems. The interaction of particles. their energy states, and the transfer of heat happen within a realm where certainty is an illusion. Our understanding of these systems is clouded by the very nature of the particles themselves. As we delve deeper into the relationship between quantum mechanics and thermodynamics, we encounter statistical mechanics, a field that seeks to bridge the gap between the microscopic world of particles and the macroscopic world we observe. Statistical mechanics embraces the uncertainty inherent in particle behavior, allowing us to describe the collective properties of systems with countless particles. It helps us understand how large-scale phenomena like temperature and pressure emerge from the chaotic dance of individual particles, each with their own uncertainties. Imagine standing on a beach, watching the waves crash onto the shore. Each wave is unique, shaped by countless variables, yet they collectively form a rhythmic pattern. Statistical mechanics allows us to view a thermodynamic system in a similar light. By acknowledging the uncertainties and probabilistic nature of individual particles, we can derive meaningful insights into the behavior of the entire system. The uncertainty principle, with its implications for energy states, sheds light on the statistical nature of thermodynamics. The principle resonates within the laws of thermodynamics, suggesting that energy cannot simply be treated as a static entity. Instead, it is a dynamic, shifting landscape, influenced by the unpredictable movements of particles. The famous physicist Ludwig Boltzmann, a pioneer in the development of statistical mechanics, captured this essence beautifully when he said, "If we have a large number of molecules, the motion of the molecules can be regarded as a random process." This acknowledgement of randomness offers a profound understanding of how macroscopic properties arise from the collective behavior of particles, each influenced by the uncertainties dictated by the uncertainty principle. As we consider the implications of uncertainty in heat and particle interactions, we find ourselves at the boundaries of what we can know. The relationships between energy states, entropy, and the behavior of particles become increasingly complex, yet they remain grounded in fundamental principles that govern our universe. The concept of energy can also be visualized through the lens of potential and kinetic energy, where particles oscillate between stored and moving energy states. This oscillation embodies uncertainty, as the exact moment a particle transitions from one state to another cannot be predicted with absolute certainty. The dance of energy is a fluid one, always in motion, and always subject to the whims of uncertainty. As we ponder the implications of the uncertainty principle, it becomes clear that our understanding of thermodynamics is enriched, not confined, by the uncertainty that pervades the quantum world. The principles of thermodynamics, which govern heat transfer and energy transformations, are not separate from the quantum realm, but rather interwoven with it. In considering the vastness of energy states and the influence of particle interactions, one might ask how this uncertainty shapes our daily lives. From the warmth of the sun on our skin to the intricate processes that power our devices, the interplay of uncertainty and energy states is omnipresent. Each moment, as we exist within this intricate web of probabilities, we are reminded of the delicate balance that defines our reality. As we journey through the realms of thermodynamics and quantum mechanics, the uncertainty principle serves as a guiding star, illuminating the paths of inquiry that lead us to a deeper understanding of the nature of existence. It invites us to embrace the unknown, to find peace within the unpredictability, and to marvel at the intricate beauty of a universe that is both ordered and chaotic. In this rich tapestry of uncertainty, we discover the threads that connect the quantum world with the macroscopic phenomena we encounter. The energy states of particles, their interactions, and the resulting implications for entropy and heat offer a window into the heart of existence itself. As we explore this interplay, we find that the uncertainty principle not only informs our understanding of thermodynamics, but also invites us to reconsider the nature of knowledge itself. In a world where certainty can often feel like an anchor, the dance of uncertainty reminds us of the fluidity and richness of existence, encouraging us to embrace the mysteries that lie just beyond our grasp. As we continue to unravel these threads, we see how the uncertainty principle influences statistical mechanics, shaping our comprehension of systems with countless particles. The very essence of statistical mechanics relies on acknowledging the uncertainties and probabilities inherent in particle behavior. This recognition allows us to derive meaningful insights into the properties of substances, illuminating the hidden connections between the quantum and thermodynamic worlds. The more we explore this intricate relationship, the clearer it becomes that uncertainty is not merely a challenge to overcome, but a vital aspect of our reality. It is a reminder that even in the complexities of scientific inquiry, there exists an underlying rhythm, a harmony that ties together the laws of physics, the behavior of particles, and the very nature of energy itself. As we stand on the precipice of understanding, the uncertainty principle serves as a beacon, guiding us through the uncharted waters of quantum mechanics and thermodynamics. It invites us to delve deeper into the mysteries of our universe, to embrace the unknown, and to find solace in the complexities that define our existence. The intertwining of the uncertainty principle and thermodynamics opens a captivating dialogue about the very nature of heat and energy transfer. At a fundamental level, heat can be perceived as the flow of energy between particles, a phenomenon that arises from their incessant interactions. Imagine a vibrant marketplace bustling with people, each one exchanging goods and ideas, creating a lively atmosphere. Similarly, the particles within a material engage in a constant exchange of energy, their movements dictating the temperature and state of the system. As we ponder the implications of uncertainty in energy states, we recognize that when particles collide, their interactions are not merely mechanical events, but a dance of probabilities. Each interaction is influenced by the inherent uncertainties within the quantum realm, making precise predictions about energy transfer elusive. This unpredictability reveals itself in the behavior of gases, liquids, and solids as they respond to changes in temperature. The energy distribution among particles shifts, leading to fluctuations in heat that are intrinsically tied to the uncertainties of their states. Consider the concept of entropy, a cornerstone of thermodynamic understanding. Entropy can be envisioned as a measure of the number of ways in which a system can be arranged, akin to a collection of books on a shelf. As entropy increases, the arrangement of those books becomes more disorderly, reflecting the fundamental tendency toward chaos in isolated systems. The uncertainty principle suggests that as we attempt to measure and define the energy states of particles, we inadvertently introduce a layer of uncertainty that influences how entropy evolves. The more precisely we know the energy state of a particle, the less we can define the overall arrangement of the system. This relationship is poignantly illustrated in the behavior of gases. Imagine a balloon filled with air. The air molecules inside are in constant motion, colliding with one another and with the walls of the balloon. The energy states of these molecules fluctuate, driven by the uncertainties that govern their behavior. As the temperature increases, the average kinetic energy of the molecules rises, leading to more vigorous collisions and a corresponding rise in pressure. The uncertainties inherent in these interactions ensure that the precise energy state of each molecule remains elusive, creating a dynamic interplay that drives the system toward higher entropy. Furthermore, the influence of the uncertainty principle on statistical mechanics allows us to derive meaningful insights about heat transfer and energy distribution. In statistical mechanics, we characterize systems by their macroscopic properties, such as temperature and pressure, while acknowledging the chaotic behavior of individual particles. This approach fosters an understanding of how bulk properties emerge from underlying quantum uncertainties. It paints a vivid picture of a world where order and disorder coexist, each shaping the other. As we reflect on the implications of statistical mechanics, we can draw parallels to the natural world. Picture a forest in autumn, where leaves flutter down from branches, creating a carpet of vibrant colors. Each leaf represents a particle, drifting to the ground in a seemingly random manner. Yet, collectively, they create a stunning display of beauty, much like how the behaviors of countless particles give rise to observable thermodynamic phenomena. The uncertainty principle, when viewed through this lens, enriches our understanding of how macroscopic properties emerge from the unpredictable interactions of countless microscopic entities. The journey through the world of uncertainty and thermodynamics leads us to consider the profound implications of these principles for our understanding of energy flows. The laws of thermodynamics, often seen as rigid and deterministic, are deeply intertwined with the probabilistic nature of quantum mechanics. The second law of thermodynamics, which states that the total entropy of an isolated system can never decrease, finds its roots in the very uncertainties that characterize particle interactions. As energy flows from areas of higher concentration to lower concentration, the inherent unpredictability of each particle's state ensures that the journey toward equilibrium is filled with fluctuating energy exchanges. In this light, the uncertainty principle not only shapes our comprehension of thermodynamic systems, but also invites us to embrace the deeper mysteries of nature. It encourages us to consider how the very act of observing an energy state can alter the dynamics of the system itself, much like how a gentle breeze can change the course of a drifting leaf. By recognizing the fluidity of energy states and the role of uncertainty, we open ourselves to a richer understanding of the universe. As we stand on the threshold of this knowledge, it becomes clear that the uncertainty principle is a vital thread in the intricate fabric of thermodynamics. It reminds us that our universe is a realm of constant change and interaction, where the boundaries between order and chaos blur. The energy states of particles, their unpredictable interactions, and the resulting implications for entropy and heat create a dynamic landscape that challenges our perceptions and deepens our appreciation for the elegance of nature. In the embrace of uncertainty, we find a pathway to deeper inquiry, a call to explore further the interplay between quantum mechanics and thermodynamics. Each question we ask unveils new avenues of understanding, encouraging us to look beyond the surface and engage with the complex realities that define our existence. As we continue this exploration, may we remain open to the wonders that await us, embracing the uncertainty that makes our journey through the cosmos so profoundly enriching. Chapter 8. Critiques and Misunderstandings of the Principle. In the realm of quantum mechanics, the uncertainty principle has often been the subject of scrutiny, leading to a tapestry of common misconceptions that can cloud its true significance. One of the most pervasive misunderstandings is the notion that uncertainty equates to a failure in measurement. This belief can obscure the profound insight the principle offers into the very nature of reality. When we think about uncertainty, it is tempting to view it as a limitation of our measuring devices or a flaw in our experimental designs. However, this perspective misses the essence of the uncertainty principle, which reveals a fundamental characteristic of the quantum world. Some aspects of nature are inherently uncertain. Imagine for a moment the process of trying to observe a small particle. As we engage in this act of measurement, we might assume that we can pin down the particle's position and momentum with precision. Yet, the more we focus on one property, the more the other eludes us. This is not merely a practical limitation. It is woven into the fabric of quantum mechanics itself. Renowned physicist Wolfgang Pauli once expressed that there is no quantum world, there is only an abstract quantum mechanical description. This perspective urges us to shift our understanding from seeing uncertainty as a glitch in our tools to recognizing it as a crucial aspect of the quantum realm. Clarifying the distinction between limits of measurement and the influence of the observer is vital in dispelling these myths. When we measure a particle, our instruments interact with it, inevitably altering its state. This interaction blurs the lines between observer and observed, challenging our classical intuitions about objectivity. Imagine a serene pond reflecting the sky above. If you were to toss a stone into the water, the surface would ripple and distort the reflection, obscuring the clarity of the image. Similarly, in quantum mechanics, the act of measurement disturbs the system being observed, shaping the results in ways that are not merely due to the imperfections of our tools, but are intrinsic to the nature of quantum entities themselves. This leads us to the critical realization that uncertainty is not a reflection of our technological inadequacies, but rather a fundamental limit that exists within the quantum framework. The uncertainty principle does not signify a failure of measurement. It embodies a deeper truth about the nature of particles and their behavior. In this light, we can appreciate that uncertainty provides us with a uniquely valuable lens through which we can explore the complexities of the universe. It invites us to embrace the unpredictable, to find comfort in the unknown. Accurate interpretations are paramount in scientific discourse, particularly when discussing the implications of the uncertainty principle. Misunderstandings can propagate and lead to misconceptions that hinder our grasp of quantum mechanics and its philosophical implications. The language we use to describe these concepts can shape our understanding and influence how they are received by both scientific and public audiences. It is essential to communicate clearly and effectively, ensuring that we do not conflate uncertainty with ignorance or negligence. Consider the implications of the uncertainty principle in the context of technological advancements. As we have seen, quantum computing exploits the very essence of uncertainty to unlock computational potential far beyond the capabilities of classical systems. This relationship underscores the importance of an accurate understanding of the principle. If the foundational concepts are misinterpreted, the innovations that stem from them may be undervalued or misunderstood. Throughout the history of scientific inquiry, figures like Niels Bohr have championed accurate interpretations of quantum mechanics. Bohr's philosophical approach encouraged a view of reality that embraced the complexities and uncertainties inherent in nature. His famous assertion that an experiment is a question which nature poses to the physicist highlights the dynamic interplay between observation and reality. This perspective is essential for fostering a more nuanced understanding of the uncertainty principle, one that acknowledges its role in guiding us through the intricacies of the quantum world. Imagining how the uncertainty principle shapes our understanding of reality invites us to reconsider our perceptions of knowledge itself. If we think of knowledge as a vast landscape, the uncertainty principle serves as a reminder that some areas remain shrouded in mystery. Instead of viewing these uncertainties as gaps in our understanding, we can appreciate them as opportunities for exploration. They beckon us to venture further into the unknown, to embrace the questions that arise from our inquiries. In the spirit of exploration, we must also be cautious of the narratives that emerge from misunderstandings. The uncertainty principle has often been sensationalized, leading to a range of interpretations that stray far from its original intent. It is common to encounter representations of quantum mechanics in popular culture that oversimplify or exaggerate the implications of uncertainty. Such portrayals can mislead audiences and contribute to the confusion surrounding the principle. Consider the portrayal of quantum mechanics in films or literature, where characters might harness the power of uncertainty to bend the rules of reality. While these narratives can be engaging, they often sacrifice scientific accuracy for dramatic flair. It is crucial to recognize that real-world applications of the uncertainty principle, while fascinating, do not grant us the ability to manipulate reality at will. Instead, they reveal the intricate dance of possibilities that characterize the quantum realm, which is both compelling and deeply respectful of the laws of nature. As we contemplate the critiques and misunderstandings of the uncertainty principle, we can draw inspiration from the words of physicist Richard Feynman, who remarked, "The imagination of nature is far greater than the imagination of man." This sentiment captures the essence of our journey into the quantum world. Nature operates on a level that often defies our understanding, challenging us to rethink our assumptions and embrace the uncertainties that lie at the heart of existence. The journey through the intricacies of the uncertainty principle is not merely an academic pursuit, it is an invitation to engage with the beauty and complexity of the universe. By clarifying misconceptions and fostering accurate interpretations, we can deepen our appreciation for the wonders of quantum mechanics. Each question we pose, each uncertainty we confront, opens a door to new realms of understanding. The act of contemplating the unknown becomes a source of inspiration, illuminating the paths we have yet to explore. In doing so, we honor the legacy of those who have come before us, the pioneers of quantum mechanics who grappled with these very concepts and laid the groundwork for future generations. Their contributions remind us that science is an ever-evolving tapestry of inquiry, where each thread of understanding is woven into a larger narrative that transcends our individual perspectives. As we reflect on the critiques and misunderstandings surrounding the uncertainty principle, we find ourselves standing at a crossroads of knowledge and curiosity. The path forward lies in our willingness to embrace uncertainty, to challenge our preconceptions, and to explore the vast landscape of possibilities that quantum mechanics offers. Each step we take on this journey enriches our understanding and deepens our connection to the cosmos, inviting us to marvel at the intricate dance of particles that shape our reality. As we continue our exploration of the critiques and misunderstandings surrounding the uncertainty principle, we encounter another common misconception: the belief that uncertainty implies a lack of knowledge or a deficiency in our ability to measure. This notion is particularly pervasive in discussions about the limits of scientific inquiry. In reality, the uncertainty principle isn't merely a statement about our ignorance. It is an affirmation of the intrinsic qualities of the quantum world itself. Imagine standing in a dimly lit room, where the shadows play tricks on your senses. You might reach out to touch an object, but the moment you grasp it, the contours and details shift in your perception. This metaphor captures the essence of quantum measurements. The act of observing a particle does not simply reveal a pre-existing state. Rather, it actively shapes the outcome. This interaction highlights a fundamental truth. The very process of measurement alters the properties of what is being measured, weaving a complex narrative about the nature of reality. This idea resonates with the insights of physicist Erwin Schrödinger, who famously illustrated the paradox of superposition. He proposed a thought experiment involving a cat that exists in a state of uncertainty until observed. The cat is both alive and dead until someone opens the box to check. This vivid imagery serves to remind us that uncertainty is not just a limitation. It is a reflection of the multifaceted nature of existence. Consider how this interplay between the observer and the observed challenges the classical notion of objectivity. In traditional physics, the observer is often seen as an external entity, separate from the system being studied. Yet, in the quantum realm, this separation blurs. The observer becomes a participant in the unfolding reality, and the act of measurement transforms the very object of study. This leads us to ponder: if our observations influence the nature of particles, what does that say about the nature of reality itself? The consequences of these insights extend beyond philosophical musings. They have practical implications in fields such as quantum mechanics and technology. As we have previously discussed, quantum computing is a vivid application of these principles. However, the broader implications of uncertainty in technology transcend mere calculations. They invite us to rethink how we approach problems and innovate solutions in an uncertain world. Imagine a future where our understanding of uncertainty shapes how we design systems, leading to more adaptive and resilient technologies. The uncertainty principle teaches us that embracing uncertainty can unlock new possibilities, enabling us to develop systems that are not only robust, but also capable of responding dynamically to unforeseen challenges. This perspective shifts our approach from one of rigid determinism to one that celebrates the fluidity of existence. Moreover, the importance of accurate interpretations cannot be overstated in the discourse surrounding the uncertainty principle. Misinterpretations can lead to oversimplifications that hinder progress in both theoretical and applied sciences. For instance, some might argue that the uncertainty principle implies a lack of predictability in quantum systems, leading to an erroneous conclusion that the universe is entirely random. Yet this view overlooks the underlying order that governs quantum behavior. While we may not be able to predict specific outcomes with absolute certainty, we can still ascertain probabilities and trends, allowing for informed predictions in a probabilistic framework. The philosopher and physicist David Bohm proposed a more holistic interpretation of quantum mechanics, suggesting that underlying order exists in the apparent chaos of uncertainty. He emphasized the importance of understanding the interconnectedness of all things, urging us to look beyond surface-level randomness to uncover a deeper coherence. Such interpretations inspire us to embrace uncertainty not as a void of knowledge, but as a space filled with potential for discovery and insight. As we navigate these complexities, we must also consider the role of popular culture in shaping perceptions of the uncertainty principle. Media representations often dramatize quantum concepts, leading to sensationalized interpretations that stray far from scientific accuracy. These portrayals can foster misconceptions that undermine public understanding and appreciation of quantum mechanics. For instance, the depiction of quantum entanglement as a kind of mystical connection between particles can lead to confounding interpretations. While entanglement is indeed a fascinating phenomenon, suggesting a form of telepathy between particles oversimplifies the underlying principles at play. It is essential to communicate these concepts with clarity, ensuring that audiences grasp the scientific realities rather than succumbing to fantastical notions that may distort their understanding. Rhetorical questions can serve as valuable tools in this endeavor, inviting audiences to engage with the material actively. What does it mean for our reality if uncertainty is woven into its very fabric? How can we harness this uncertainty to foster innovation and progress? By encouraging reflection, we create space for a deeper exploration of the uncertainty principle and its implications. In contemplating the uncertainty principle, we find ourselves reflecting on the broader themes of knowledge, perception, and reality. The complexities of quantum mechanics challenge us to reconsider our definitions of certainty and truth, urging us to embrace ambiguity as a vital aspect of the human experience. As we move forward, it is crucial to honor the legacy of those who have paved the way in our understanding of quantum mechanics. Their dedication to unraveling the mysteries of the universe inspires us to continue exploring the vast landscape of possibilities that the uncertainty principle offers. Each inquiry, each uncertainty we face, serves as a stepping stone toward a more profound understanding of our place within the cosmos. In this continuous journey, we are reminded that uncertainty is not a barrier to knowledge. Rather, it is a gateway to deeper insights. By embracing the complexities and nuances of the uncertainty principle, we open ourselves to a richer understanding of reality, inviting us to marvel at the wonders that lie beyond the horizon of our comprehension. Chapter 9. The Uncertainty Principle in Future Physics. In the ever-evolving landscape of physics, the uncertainty principle continues to cast its shadow, inviting us to explore the depths of quantum mechanics and beyond. As we peer into the future, we find ourselves at the cusp of potential developments that could reshape our understanding of uncertainty itself. What might these advancements reveal about the quantum world that has eluded us for so long? The pursuit of knowledge in this realm is akin to sailing into uncharted waters, where each wave brings new insights and challenges. Emerging theories suggest that the uncertainty principle may not be a fixed boundary, but rather a gateway to deeper explorations of reality. Imagine a garden where new flowers bloom, each representing a different perspective on quantum phenomena. Some physicists propose that the intricacies of quantum entanglement could hold the key to unlocking a more profound understanding of uncertainty. Could entangled particles, which maintain a mysterious connection regardless of distance, hint at a reality where uncertainty is a natural byproduct of interconnectedness? As we contemplate these possibilities, the implications of the uncertainty principle extend into new paradigms of physics. The principle has already challenged classical notions of determinism, inviting us to consider a universe where probabilities reign supreme. In this space, traditional views of causality may shift, leading us to question What does it mean for an event to be determined? The answers to such questions may lie in the heart of future explorations, where the boundaries of quantum mechanics blur with other fields of study. An intriguing area of speculation is the quest for a theory of quantum gravity, which seeks to reconcile the principles of quantum mechanics with the fabric of spacetime, as described by general relativity. Picture spacetime as a vast ocean, where the waves of energy and matter interact in intricate patterns. The uncertainty principle may play a pivotal role in this synthesis. As physicists grapple with the nature of black holes and singularities, they confront the limitations imposed by uncertainty. How do we describe a particle's position and momentum near the event horizon of a black hole? The answers may not only redefine our understanding of gravity, but also challenge our very concepts of space and time. In this quest, luminaries like Stephen Hawking have pondered the implications of these ideas. Hawking once remarked, "The black hole is not the end but the beginning of our understanding." This perspective invites us to consider that the mysteries of black holes, coupled with the uncertainty principle, may open doors to new theories that transcend our current understanding of physics. As we journey further into this uncharted territory, we encounter the notion that spacetime itself could exhibit quantum properties. Imagine a fabric woven from the threads of uncertainty, where each point in space may possess its own quantum state. This challenges our classical view of a smooth, continuous spacetime, suggesting instead a granular structure that aligns with the inherent uncertainty of quantum mechanics. What would such a reality imply for the laws of physics as we know them? This tantalizing question invites us to envision a world where the very fabric of existence is shaped by the delicate interplay of uncertainty and reality. Moreover, as we explore the implications of the uncertainty principle in the context of quantum gravity, we are led to consider the nature of time itself. Is time a flowing river, or could it be a series of discrete events shaped by the uncertainties of quantum interactions? The philosophical ramifications of these speculations are profound, as they challenge our understanding of existence and the continuity of experience. In the pursuit of a unified theory that encompasses both quantum mechanics and general relativity, scientists are beginning to explore concepts such as loop quantum gravity and string theory. Picture a symphony, where each instrument plays a unique part in creating a harmonious whole. These new theories aim to bring together the principles of uncertainty with the dynamics of spacetime, potentially revealing a richer, more intricate reality. The implications of these emerging theories are not merely theoretical musings. They hold the potential to reshape our technological landscape as well. Quantum computing, which we touched upon in previous discussions, relies on the principles of superposition and entanglement, both of which are deeply intertwined with the uncertainty principle. As we push the boundaries of quantum technology, the very essence of uncertainty may become a tool for innovation, allowing us to tackle problems previously deemed insurmountable. As we consider the trajectory of future physics, we are reminded of the words of physicist Richard Feynman, who stated, "The more you look at the quantum world, the more you realize that it is different from our usual intuitive way of thinking." This sentiment encapsulates the journey we are on, a journey that invites us to embrace the strangeness and beauty of the quantum realm. In this exploration of the future, the uncertainty principle emerges as both a challenge and a source of inspiration. It beckons scientists and thinkers alike to delve deeper into the mysteries of existence, to question our preconceived notions, and to embrace the uncertainty that lies at the heart of reality. What wonders await us in the uncharted territories of quantum mechanics? The answers may reshape not only our understanding of the universe, but also our place within it. As we move forward, the interplay between uncertainty and knowledge may forge new paths in our quest for understanding. Perhaps the future of physics will reveal that uncertainty is not merely a limitation, but a fundamental characteristic of the universe, one that fosters creativity, exploration, and discovery. What if, instead of viewing uncertainty as an obstacle, we embraced it as a vital element of our universe's design. Imagining a future where the uncertainty principle is not only understood but celebrated opens up a realm of possibilities. The interplay of quantum states and the ever-shifting landscape of space-time may inspire new technologies, from advanced computing systems to innovative energy solutions. It invites us to consider how our understanding of the universe can evolve, fostering a deeper connection with the cosmos and each other. In this unfolding narrative, we find ourselves woven into a grand story, a story that challenges our perceptions and invites us to reflect on our journey through uncertainty. As we look toward the horizon, we are reminded that the pursuit of knowledge is a path paved with questions, each leading us to deeper insights and revelations. What lies ahead could be a future where uncertainty is not merely a principle of quantum mechanics, but a guiding light illuminating our way through the intricate maze of existence. The uncertainty principle, with its profound implications, continues to inspire curiosity and wonder. It invites us to engage with the mysteries of the universe while acknowledging the limitations of our understanding. As we take this journey together, we are reminded that the essence of life may very well thrive in uncertainty, and in that thriving we may discover the beauty that lies in the unknown. As we immerse ourselves in the exploration of quantum gravity, we encounter a fascinating intersection where the uncertainty principle and the very nature of space-time converge. Imagine space-time as a dynamic stage where the fundamental forces of the universe play out their intricate dramas. The quest for understanding how gravity operates on a quantum scale invites us to rethink the very structure of this stage. Could space-time itself be influenced by the uncertainties inherent in quantum mechanics? One emerging theory suggests that space-time may not be a continuous entity but rather a mosaic of discrete elements, akin to the pixels on a digital screen. This hypothesis aligns with concepts found in loop quantum gravity, which proposes that space-time is quantized. Visualize space as a vast network of interconnected loops, each representing a quantum state. In this framework, the uncertainty principle may dictate that the exact nature of any point in space-time is shrouded in a veil of uncertainty. Such a perspective challenges our traditional understanding and raises profound questions about the fabric of reality itself. How might our perception of time and distance transform if the very essence of space-time is subject to the uncertainties of quantum mechanics? Moreover, as we unravel these threads, we find ourselves contemplating the implications for causality and the nature of events. In classical physics, we often regard events as linear sequences, where one action leads deterministically to another. The introduction of quantum uncertainty, however, invites us to consider a more fluid interpretation of causality. Could events be interconnected in a web of probabilities, where outcomes are not strictly determined but rather shaped by the interplay of uncertainties? This notion resonates with the ideas of physicist David Bohm, who proposed a holistic view of the universe, suggesting that everything is interconnected in a vast, implicate order. As we reflect on these emerging ideas, we are led to ponder the implications for our understanding of reality. What if the universe is not merely a collection of isolated events, but a living tapestry, where each thread influences the others in ways we have yet to comprehend? In this vision, the uncertainty principle becomes not just a limitation of measurement, but a fundamental characteristic of the universe itself, shaping the contours of existence. Additionally, the exploration of quantum gravity may illuminate the mysteries of black holes and their relationship with the uncertainty principle. When we consider the enigmatic nature of black holes, we confront questions that challenge our understanding of physics. For instance, what happens to information when it crosses the event horizon? The uncertainty principle suggests that our attempts to measure or observe phenomena in such extreme environments are inherently limited. Yet could the interplay of uncertainty and gravity lead us to new insights about the fundamental nature of information in the universe? Renowned physicist Juan Maldacena has proposed ideas that intertwine black holes and quantum mechanics, suggesting that the information encoded on the event horizon may be preserved in a way that defies our classical intuitions. Imagine a holographic universe, where the three-dimensional experiences we perceive are merely projections of information encoded on a two-dimensional surface. This radical perspective invites us to rethink our notions of space and information, as well as our understanding of what it means to know something in the context of quantum mechanics. In contemplating these theories, we find ourselves drawn to the idea that the uncertainty principle could inspire new perspectives on the nature of reality. Rather than seeing uncertainty as an obstacle to knowledge, we might embrace it as a doorway to deeper understanding. Could it be that the most profound insights arise not from certainty, but from the embrace of the unknown? Perhaps the future of physics will reveal that uncertainty is not merely a feature of quantum mechanics, but a guiding principle for our exploration of the cosmos. As we gaze into the horizon of future physics, the uncertainty principle remains a beacon, illuminating pathways to discovery and innovation. The potential for new technologies grounded in quantum mechanics stretches far beyond our current imagination. Concepts like quantum teleportation and quantum networks promise to revolutionize communication and information processing. Imagine a world where information is transmitted instantaneously across vast distances, transcending the limitations imposed by classical communication methods. Such advancements might change the very fabric of our society, fostering deeper connections and understanding among humanity. In this unfolding narrative, we are reminded that the journey through uncertainty is not merely a scientific pursuit, but a deeply human experience. As we navigate the complexities of existence, we are called to embrace our curiosity and wonder. What new realms of possibility await us as we continue to explore the mysteries of the universe? The answers may challenge our perceptions and inspire us to see the beauty in the unknown. As we reflect on the interplay between the uncertainty principle and the quest for a unified theory of physics, we find ourselves at a crossroads of imagination and inquiry. Each question we ask propels us further into the depths of understanding, revealing the intricate connections that bind us to the cosmos. What if our journey through uncertainty is the very essence of what it means to be alive, an exploration that fuels our desire to learn, to grow, and to connect with the universe around us? The future of physics, illuminated by the uncertainty principle, beckons us to embrace the unknown with open hearts and curious minds. We stand on the threshold of discovery, poised to unlock the secrets of existence and forge new pathways toward understanding. What awaits us in this vast expanse of uncertainty? The possibilities are as boundless as the universe itself, inviting us to dream, to question, and to explore the beauty inherent in the unknown. Chapter 10. Embracing the Unknown. Lessons from Uncertainty. In the realm of quantum mechanics, the uncertainty principle invites us not only to accept the inherent unpredictability of the universe, but also to embrace it. This principle encourages a mindset that is open to the unexpected and flexible in the face of ambiguity. Imagine standing before a vast expanse of shifting sands, where each grain represents a potential outcome. The more we grasp at one grain, the more others slip through our fingers. This vivid imagery encapsulates the essence of uncertainty, urging us to explore without the confines of rigid expectations. Uncertainty has a profound impact on scientific inquiry and exploration, acting as a catalyst for discovery. When scientists engage with the unknown, they must navigate the unpredictable terrain of their own hypotheses. Each experiment, each observation, becomes a doorway to new knowledge, albeit one that may lead in unforeseen directions. Think of the pioneering work of physicists like Richard Feynman, who once remarked, "The imagination of nature is far greater than the imagination of man." This observation highlights how uncertainty can lead to breakthroughs that challenge our understanding of the universe. When we step into the arena of the unknown, we open ourselves to possibilities that extend beyond our current grasp. Imagine the thrill of uncovering a new particle or phenomenon, a discovery that transforms our understanding of the cosmos. In embracing uncertainty, scientists foster a culture of inquiry that thrives on questions rather than answers. Each question serves as a spark, igniting curiosity and leading to further exploration. This interplay between uncertainty and inquiry is evident in the field of quantum mechanics, where the very act of measurement alters the state of the particles being observed. The unpredictability inherent in these interactions reminds us that knowledge is not a destination, but an ongoing journey. Philosophically, the relationship between knowledge and ignorance in science presents a complex tapestry that reflects the human experience. As we seek to understand the universe, we grapple with the limitations of our own perceptions. The uncertainty principle serves as a metaphor for life itself, revealing that certainty is often an illusion. Imagine standing on the precipice of a great cliff, gazing out into the vast unknown. The churning sea below symbolizes the myriad uncertainties we face in our lives. Just as we cannot predict the precise moment a wave will crash, we cannot foresee the twists and turns that life may take. The interplay between knowledge and ignorance invites us to acknowledge our limitations. Albert Einstein famously stated, "The more I learn, the more I realize how much I don't know." This sentiment resonates deeply within the scientific community. As researchers delve deeper into the mysteries of the universe, they uncover layers of complexity that challenge their previous understandings. Each revelation opens new avenues of inquiry, yet simultaneously reminds us of the vast expanse of what remains unknown. The uncertainty principle then becomes a profound metaphor for navigating the unpredictability of life. It teaches us that while we may strive for clarity and certainty, the essence of existence is often steeped in ambiguity. Picture a winding river, its course ever-changing, shaped by the landscape around it. Just as the river flows, adapting to the contours of the earth, so too must we adjust our expectations in response to the unpredictable currents of life. In this dance with uncertainty, we learn invaluable lessons about resilience and adaptability. The world is full of surprises, and our ability to embrace them can lead to personal growth and discovery. Consider the journey of scientific pioneers who faced skepticism and doubt, yet persevered in their pursuit of knowledge. Their stories remind us that the path to enlightenment is rarely straight. It often twists and turns through uncharted territory, requiring courage and determination. Embracing the unknown allows for innovation and creativity to flourish. In the scientific community, moments of uncertainty can lead to groundbreaking ideas and revolutionary technologies. Imagine the initial hesitation of researchers exploring quantum computing, a field that challenges traditional notions of computation. As they ventured into the realm of qubits, they encountered a landscape where uncertainty became an ally rather than an adversary. This willingness to embrace the unknown has the potential to redefine our technological landscape, much like the transformative discoveries of the past. As we reflect on the uncertainty principle, we can see its echoes in our daily lives. Each decision we make is steeped in uncertainty, shaped by countless variables that lie beyond our control. Picture a moment of choice, where the outcomes branch out like the limbs of a tree, each path leading to a different destination. The act of choosing requires us to confront our uncertainties, acknowledging that the future is inherently unpredictable. In this context, uncertainty can be viewed not as a source of anxiety, but as an invitation to explore and engage with the world around us. By cultivating a sense of wonder and curiosity, we can approach the unknown with open hearts and minds. The lessons we learn from uncertainty can serve as guiding lights, illuminating our path through the complexities of existence. As we continue to unravel the mysteries of the universe, we are reminded that knowledge is not an endpoint, but a continuous journey of exploration. The uncertainty principle teaches us to be comfortable with the unknown, to find beauty in ambiguity, and to embrace the possibilities that lie ahead. Imagine a garden of ideas blossoming in the mind, each flower representing a different avenue of thought, nurtured by the fertile soil of uncertainty. This garden of exploration encourages us to ask questions, to seek understanding, and to celebrate the richness of our experiences. The uncertainty principle, in its essence, reflects the magnificent complexity of the universe, a universe that invites us to embrace the unknown with open arms. As we venture forth into the intricate dance of life, let us carry with us the wisdom gleaned from uncertainty, allowing it to guide our steps as we navigate the uncharted waters of existence. In the spirit of scientific inquiry, we are called to confront our uncertainties with courage and curiosity. Each question we ask has the potential to unveil new layers of understanding, revealing the intricate web of connections that bind us to the cosmos. Imagine standing at the edge of a forest, where the trees represent the vast body of knowledge, and the paths leading into the underbrush symbolize the unknown. Each step into that forest is an act of faith, an exploration of possibilities that may transform our understanding of both the world and ourselves. The uncertainty principle reminds us that uncertainty is not to be feared but embraced. It is a testament to the complexity of our universe, a universe that thrives on unpredictability and surprise. As we journey through life, let us remain open to the unexpected, allowing our experiences to shape us in ways we cannot yet imagine. The lessons gleaned from uncertainty enrich our lives, urging us to explore the depths of our potential and the breadth of our experiences. In the grand tapestry of existence, uncertainty weaves its threads through every aspect of our lives. It teaches us that while we may seek answers, the journey itself is where the true beauty lies. Let us embrace the unknown, welcoming the lessons it brings, and nurturing the curiosity that drives us to explore the wonders of the universe. With each step into the unknown, we honor the legacy of those who have dared to seek, innovate, and discover, paving the way for future generations to embark on their own journeys of exploration and understanding. Uncertainty, while often perceived as a hindrance, can also be a profound source of inspiration in the scientific realm. It nudges researchers to push boundaries and dare to question the status quo. Consider the journey of Marie Curie, who ventured into the uncharted territory of radioactivity at a time when the scientific community was largely skeptical. Her relentless pursuit of knowledge amidst uncertainty led to groundbreaking discoveries that transformed our understanding of atomic science. Curie's work exemplifies how the unpredictable nature of scientific inquiry can yield extraordinary insights, ultimately shaping fields far beyond her own. Imagine standing in a laboratory surrounded by complex instruments, each poised to unveil the mysteries of the microscopic world. Every experiment is a leap into the unknown, where the results may defy initial expectations. The uncertainty that accompanies this exploration fosters an environment of creativity and innovation. It encourages scientists to embrace the unexpected outcomes, for these moments often lead to radical new ideas and technologies. In a world that values certainty, the uncertainty principle serves as a reminder that the unknown is not something to shy away from, but rather an integral part of the scientific process. This idea is echoed in the words of physicist Max Planck, who noted, "When you change the way you look at things, the things you look at change." This shift in perspective allows us to see uncertainty not as a barrier, but as a doorway to new realms of understanding. Philosophically, the uncertainty principle invites deep reflections on knowledge and ignorance. As we embrace the unknown, we are often confronted with the limitations of our understanding. The interplay between what we know and what we do not know becomes more pronounced. Picture a vast library filled with shelves of books, each representing a different aspect of knowledge. Yet for every book read, there are countless volumes left untouched, symbolizing the vast realms of ignorance that persist. This metaphor beautifully encapsulates the nature of scientific inquiry, an endless journey where each discovery opens doors to new questions. As we contemplate the essence of knowledge, we may ask ourselves, how can we find comfort in this vast sea of uncertainty? The answer lies in recognizing that uncertainty itself is a catalyst for growth. It compels us to adopt a mindset that values inquiry over conclusion, exploration over certainty. This philosophical stance aligns with the scientific method, which thrives on questioning and revising our understanding based on new evidence. The uncertainty principle, in its essence, becomes a metaphor for life's unpredictability. Just as particles exist in a state of potentiality until measured, our lives are often shaped by unforeseen events and choices. Imagine a winding path through a dense forest, where each turn holds the promise of new discoveries. Some turns may lead us to unexpected beauty, while others may present challenges we must navigate. Life, like quantum mechanics, is replete with uncertainties that can lead to profound transformations. Embracing the unknown invites us to cultivate resilience. It teaches us that failure is not the end, but rather a stepping stone on the path to success. Much like the trials faced by Thomas Edison, whose countless experiments with electricity led to the invention of the light bulb, we learn that perseverance in the face of uncertainty can lead to extraordinary breakthroughs. Edison's journey epitomizes the idea that embracing uncertainty can illuminate new paths forward. In the grand scheme of things, the uncertainty principle encourages us to cherish the journey of discovery, both in science and in life. Each moment holds the potential for revelation, and every question posed can lead us deeper into the heart of understanding. As we stand at the intersection of knowledge and ignorance, we are reminded of the beauty that lies in the exploration of the unknown. Picture the night sky filled with countless stars, each representing a question yet to be answered, a mystery waiting to unfold. In this luminous expanse, we find a sense of calm amidst the chaos of uncertainty. The stars guide us, reminding us that while we may not have all the answers, the quest for knowledge is what enriches our experience. Just as the cosmos is vast and unknowable, so too is our journey through life, a journey that can be embraced with wonder and curiosity. As we weave together the threads of uncertainty and inquiry, we discover that the uncertainty principle resonates far beyond the confines of physics. It speaks to the heart of our human experience, inviting us to confront our fears and to view the unknown as an opportunity for growth. Imagine standing on the brink of a new adventure, your heart racing with anticipation. The unknown holds promise, beckoning you to take that first step forward, to explore the possibilities that lie ahead. Ultimately, the uncertainty principle teaches us that life, much like quantum mechanics, is a delicate balance of certainty and unpredictability. It urges us to embrace the unknown with open arms, to find solace in the questions that propel us forward. As we continue our journey through the complexities of existence, let us carry the lessons of uncertainty close to our hearts, allowing them to guide us as we navigate the ever-changing landscape of our lives. Each twist and turn presents a chance for discovery, a reminder that the beauty of life lies in its unpredictability.